Hello everyone, today in this video we'll be discussing the first module of 18 CS61, and this is the first subject in the 6th semester, which is system design and compiler. Okay, so in this subject we have the like computer organization, those things were there, right? Like addressing modes and all, registers. So those things will be discussed in a further depth here, like what code is used for what. So for this subject it's not like you will be just going through and like theory subject and all. It's not that easy because there are many things which you need to understand in depth. So the first PDF only, if I tell you, like it's around 100 pages. Okay, I've purposely kept it in a very depth because understanding the first module is important, because if you don't understand the first module, the rest of the modules also you won't understand. Okay, it's just like automata. In the previous semester, in the third semester we had ADE, and in the fourth semester we had design and analysis of algorithms. So like those subjects, this is the most important subject of sixth semester. Okay, so after this, the next important one is the computer graphics. Okay, so I request you to open this PDF in another device to refer when I am referring this PDF, because it's required. I'll be changing the slides very frequently. So yeah, that's the basic introduction of this subject, and the topics are as follows. The first is about what is system software. See, basically you have like this system. Okay, this is the system, and inside the system there are two things. One is the inbuilt things, and the other is the applications which you load. Okay, the inbuilt things include those compilers and all, assemblers, registers, memory address and all. Those things are the inbuilt things. Okay, without those things the system won't run itself. Okay, but the application part and all which you load, like calculator and all, those are the things which you externally load. Without these things also the computer will run. Okay, so this is the main difference between system software and application software. Okay, this is one of the important questions from exam point of view. Okay, so I'll be discussing what are the important questions after a few moments. So let's go through the syllabus first. Here we have the machine architecture of SIC and SIC XE. This is also very important from exam point of view. Like what all points you need to mention, everything will be discussed in detail. So have patience, watch the video till the end to get a in-depth understanding of the first module. And after that we have the basic assembler functions. We have 5 things here. Okay, and this is a small topic, and this is the introduction of what is the assembler functions. And here we have 2 things. One is dependent assembler functions and another one is independent assembler functions. And this is also not that important. Here also 5 subtopics are there that you can easily means get to know. It's just the theoretical concepts. And here is the main important thing of the means this module. Okay, because in the exam also they have asked like to convert the program into the object code. So there are few steps you need to very carefully understand, very precisely understand what changes you need to make in each for each line of code. Okay, so let me give you the the overview of the question paper, like the previous questions, how they have asked the questions. So this is about the first topic, explain in detail SIC XE and SIC machine architecture. See how many times it's repeated, 5 and 2, 7 times it's repeated. Okay, and the most important one is SIC XE. Okay, this is the basic one, this is the extra equipment one. Okay, means the advanced version of SIC. Okay, this is the very important question. And this is about the program, writing a program, that also we'll discuss how to write the SIC programs. And comparatively it's not that important, but if you know, it's better for you, because if it in exam it comes, you can write that. Okay, and write an algorithm for the pass 1 pass 2 of an assembler. This is also very important. There are 2 algorithms, I'll be discussing that. And generate an object code. See, this is what I was talking about. SIC XE's object code will be asked for like in the exam. Okay, so here what you are supposed to do is you need to know how to convert these things. What do these symbols mean? What is the first column, second column and third column? What do these things represent? Why it is hash here? What does hash represent? This is which type of addressing mode? And what will happen if I like write comma here? And what is this label here? What does it do? What is JLT? When it gets repeated? All those things you need to know in very depth. Okay, that's why the PPT means this PDF is a bit in depth, to get a basic understanding of all these things, so that it won't cause a problem in the further modules. Okay, so it's very important that you get to know the things very clearly in the first module itself. Okay, So this is that one of the type of the question which could be asked in exam, and here the mnemonic codes will be given, opcodes will be given. You have to convert this and write the object program. Okay. And this is another one important question, right? Define system software, distinguish between system software and application software. And the next important question is this is from the last topic, bootstrap loader. There is an algorithm for it. And the next one, these topics are from the remaining topics which I have not talked about. And this is another type of question, generate the machine code. Here also these things will be given. You will be supposed to write a code. So to write a code, you will need to be very thorough with the basic concepts. Okay, that's why I'm telling, listen carefully. Okay, here also another SIC program, like in the second question also we had, right? Like write an SIC program for the following. Write an SIC program to calculate delta is equal to alpha plus beta into gamma minus 10. Okay, like that only the SIC program is asked. And the next important, this is also another question, write the object program. So these things will be given, you are supposed to write the program. Okay, and that's all. What are the topics, important topics in the module? So even you see what I'll tell you honestly, like if you start watching this video and start from the beginning till 70% of the video is over, you won't understand anything. Okay, just listen carefully, because when after 70% of the video is over, see what I mean is, this is the total video. Okay, till 70% it's just the basic things. You will be just learning what are the addressing modes and all. You will feel it as a waste. Okay, but once you listen this part carefully, after that when you come to the practical application, writing the programs part, at that time you will be remembering, this was done in the video, this was done. At that time this will be helping you. Okay, so it's very important that you watch this video. Even if you don't understand anything, just watch it. Okay, just watch it at least one time. Okay, then even if you don't watch, it doesn't matter much, because when you come here and when you see the things again, you have to refer back multiple times. Okay, but if you watch once, that's sufficient for you. You need not refer back as many times as you have to refer back if you don't watch this part. Okay, so that's some of the things which I had to tell you. And let's go to the flow of the video. So first I'll be discussing what are the differences between the system software and application software, an important question from exam point of view. So this is the software here. There are two things here, inbuilt things and the application things. You just have to write the differences in it. Okay, it's like 6 to 7 marks in exam. Okay, and the next one is SIC architecture and SIC architecture. To design an assembler, you need to have an architecture, right? So there are two types of architecture. In that there will be memory, registers, and many other things will be there. So that we will be discussing, and you have to write define each of these, like memory, register and all. Okay, after these two things, you need to know how to write the SIC program, because as I had discussed in the previous paper, those are asked in the exam to write the SIC and programs. And after that, the next half of the module is dealing with the assemblers. In assemblers we have mainly 4 topics. Okay, this is the first one, second one, and this is the third one, this is the fourth one. Okay, so in assembler, the basics, what are the users, advantages, disadvantages, what are the basic codes which are used in the assembler. And after that, to convert the SIC program to operation code, and after that to object program, it is object code and object program. Okay, this is the flow which you need to know, because they will give you this thing and they'll ask you to write this thing. Okay, for that you need to know. And algorithms are there, 2 algorithms which you need to know. It's discussed in brief in the first part. And SIMTAB, OPTAB and basics, those things, what are the tables used. So the first part is dealing with the basics of assembler, and the next 2 parts are nothing but the dependent and the independent assembler features. So here the detailed 2-pass algorithm is there, and here the 5 theoretical things is there. This is very easy as compared to this one. Here the numerical will come. Okay, convert the opcode and the op program, which I showed you in the question paper, right? Like this thing. Okay, this what is the thing which you are expecting. This is the SIC program. This program should be converted to object program. That will be dealt under the topic machine dependent assembler features. Okay, and after that we have 2 small topics, program relocation and modification, that also will be discussed. And finally we have the type of assemblers, 1-pass and multi-pass, and some theory and the numerical things are this is very simple. Okay, and finally we have the loaders, basic architecture and algorithm for bootstrap loader, because in exam they have asked algorithm for bootstrap loader. You need to know like a brief overview of the algorithm and how the loading works. After the object program is ready, how it's loaded into the memory, that loading part you need to know. So that's what it's discussed in the fifth part. Okay, so this is the flow of the video, and let's get started with the actual thing. Let's get started from the what is software. Okay, this is the basic thing, what is software. So mainly for any computer system, in computer domain, if you come, there are two things. One is hardware part and another one is what, software part, right? Hardware part is that which we can like physically touch, and software part is that which is internally present inside the computer, like the application programs and all. That is known as software. Okay, software refers to the set of electronic program instructions or data a computer processor reads in order to perform a task. Okay. And coming to the categories of software, there are two types of software, as I have already told you: system software as well as the application software. Okay, system software is the inbuilt things, and application software is that which you load externally. Okay, these two things are the divisions of types of software. Okay, so if you see here, the hardware parts are like CPU, mouse, etc., which you can physically touch. System software includes the operating system and the utility libraries and all, which are inbuilt. Without that, the computer won't work. And the application software are just the application like your games and all, camera. Okay, those things are the application software. So this is the basic graph, or means the diagrammatic representation of the different types of software. And this is the thing which you need to write in exam if they ask you for a difference between system and application software. Okay, so here in the system software, you have like, what are the main differences? System software is a set of programs to manage the computer. To manage the computer resources, you need to have the system software. But application program is used to perform the group of functions. For a specific purpose it's written, and this for the working of computer. Once the computer works, what task the computer needs to perform, that you will be specifying here. Okay, that is the first difference. The second difference is it's written in a low level language, because it's dealing with the internal part of the computer, so it's in a low level language. And this is written in a high level language, like the applications and all. The user end programs are means usually written in high level language only, right? That's the second difference. And third difference is it starts running when the system is turned on, and this runs only when the user executes. Like if you have on the system but you have not played any game as of now, executed any gaming application, it won't run, right? It will stay there itself. But when you turn on the system, at that time only the operating system, bootstrap loader and all those things will come, right? So this is the third difference. The fourth difference is the system can't run without the system software, whereas a system does not require application software to run. Okay, this is independent of the system software, this is dependent on the system software. It is for general purpose, like a computer should run for general purpose it's used, and this for the specific purpose, means the application has a specific purpose, like calculator is used for calculating, notepad is used for writing the notes, and so on. Okay, so some of the examples which you have to give in the sixth part is the operating system, assembler, compiler, loader, and linker. Here we have the applications, you can write any application names. And the last one is it's machine dependent and it's not machine dependent, because application software can be installed in any of the devices, right? But the machine dependent means the particular features of the machine will be there, it will be applicable for a specific machine only, right? For example, MacBook is here, and another one, the Samsung laptop is here. Okay, some features will be different here, some features will be different here, like 32-bit, 64-bit and all. So if you like take this RAM and put here, it won't work, but the same application will work. Like camera will work here as well, and camera will work here as well, right? So that's the difference between machine dependent and not machine dependent. This is the question which is the important one, like it's asked for 7 marks, which in the previous papers. So go through it before your exam. Okay, the next one, system software and machine architecture. This is a small topic. So the machine architecture, there are two things, one is dependent and another one is independent. Okay, machine is divided into two parts, one is dependent and another one is independent. Okay, so in the dependent part, we have the machine code, instruction format, addressing mode, register, because these things differ from computer to computer. Whereas the code optimization, subprogram linking, and the logic of the code, that things don't change from the system to system. The logic will be same only for the code, only the syntax will differ, right? So that's what the difference in the dependent and independent. Okay, so moving on, we have the next one, which is SIC, simplified instruction computer. SIC first we'll discuss, then we'll discuss SIC XE. So the first half of the module will be over. In the second half, we have the assemblers, which we'll be discussing. Okay, so let's discuss what is SIC and SIC XE. This is very important for you to understand to write the object programs. Okay, So what does SIC mean? SIC is a simplified instructional computer. Okay, so why we need simplified instructional computer is because there are many computers around the world and they have the different specifications. Okay, like different RAM and all, different compilers, different addressing modes and all. So many things are different. So which one we will specifically learn? If we learn this one only, we won't understand this one and this one. If we learn this one, we won't understand this one and this one. So for that, what they have done is they have taken the common things in all of this. Okay, means majorly what are the most common things occurring in these three computers, that they have taken and they have made a hypothetical computer. This is the imaginary computer which they have means designed, and in that all the common features of the computers around the world that is present here, and this we will be learning. So this serves as a basic foundation for the computers, right? If you understand this system, you will understand what is common in all of these systems. So let's understand what is the basic foundation for each computer. Okay, so every machine architecture includes memory, registers, data formats, instruction format, addressing modes, instruction set, input and output. So if they ask you an exam, you have to mention all these points and mention the examples as well as the definitions. What do these things mean? Give some examples. Okay, so we'll be discussing that in this video. Okay, so the first thing is memory. Okay, so every computer will have memory, right? So memory consists of 8-bit bytes. Okay, so how it is arranged? It is arranged in the form of bytes. Suppose that this is the memory here. So in the memory you will have each byte here, 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. Okay, and 1 byte consists of how many bits? 8 bits. Okay, what is bit? Bit is nothing but 0 or 1. This is 1 bit, this is 1 bit. Like that, if you write 8 times, that can be stored here. That is the structure of the memory. Okay, 8 bit will be considered means for 1 byte. Okay, if these are the bit storages, this is known as 1 byte. So memory consists of 8-bit bytes. 8 bits byte, in that form the memory is stored. Okay, how many bytes your computer is of, like 64 KB, 10 GB and all those things will be there, right? So that is known as bytes. Okay, and any 3 consecutive bytes form a word. You need to understand what is word. Word is nothing but 3 times you take byte. This is 1 byte, another byte, another byte. This is known as a word. Okay, word is of 24 bits. This is 8 bits, 8 bits, 8 bits. So 24 bits form a word. Okay, these things you need to understand. All addresses on SIC are byte addresses because they are starting from byte. This is byte 0, this is byte 1, this is byte 2. So they are addressed using bytes. Okay, and there are total of 32768, which is nothing but 2 power 15 bytes in the computer memory. Okay, in the computer memory of what we have considered as a hypothetical computer, in this computer, considering SIC, not SIC XE. Okay, SIC XE will have a bit greater means total memory. In SIC, what computer we have considered hypothetically, it has how much storage? 32768 bytes, that is 2 power 15 bytes. Okay, so this is about the memory which you have to write. The first thing which you have to define is memory, and these are the points which you have to write. Okay, in the same we will be discussing the next one as well. What is register? Register is register is nothing but a variable. Okay, register is a space where you can store some value. Okay, so this one register, like let's call it register R, and if you want to perform like an operation 1 plus 1 is equal to 2, at that time what you will do is you will take a register, store 1 here, and after that you will perform addition operation on this same register, and the register will ask addition operation on which operand I should perform. You will specify the next operand. So this will be getting added here, and 1 will be overwritten with the additions result. So 2 will be written here, and that will be stored in the same register. Now you can use this register for storing in the memory, or you can use this for displaying the value. You can use this as a temporary register. So understand one thing, register is nothing but a empty box. Okay, register is nothing but an empty box where you can store the values. Okay, so there are different types of registers for different purposes. Okay, so if you want to perform the addition operation, you will be using the accumulation register. Okay, means all the arithmetic operations, plus, minus, into, divide, all these things use the accumulation register. Okay, the next one is there are registers I have written here. So I think the next one is the linkage register, and also there are many registers. Okay, X register is also there, and another one is SW register. So what happens is let's make it simple. There are 2 registers. Okay, this is A register, this is X register. Okay, so what happens is these are the codes which I have written. So if you know the C programming, it will be like int C. Okay, int C is equal to 1, C plus is equal to 1, C out C. Okay, C out C. So C will be displayed. So what's happening here? C's value is getting stored here. So when you write int C, assume that C is this. Okay, this is only C, 1 will be stored here. Okay, Then you are doing C plus is equal to 1. So C's value is getting incremented here, and that is stored as 2, and you will be Couting C. What is value here? That will be displayed in the screen. Now what is this register used for? This register is used for where the instruction is pointing. This is pointing to this location, like suppose 1000, so it is pointing here 1000. Okay, the next instruction 1002, so this will get incremented to 1002 when this is over. When this is also over, this will increment it to 1004, and that then the program will over. So different type of register are used for different purposes. Okay, this you'll understand more. See, what are the things I already told you. Till 70% of the video it won't seem relevant, but the thing is you need to listen to this. Okay, after 70% of the video everything will start getting means in their positions, means it will make sense to you. Okay, so till 70% of the video just watch the basic parts. Okay, so there are total 5 registers which have the special uses, like I'll be discussing what are the 5 special registers, and each register is 24 bits. That means one word. Okay, each register will have one word space. One word space means 8 bits here, another 8 bits here, another 8 bits here. Fine. So these are the 24 bits, and this for the each register. And the table shows the mnemonic number and uses of the each register. So now let's see what are the different types of register. Okay, so these are the 5 registers which are in SIC. Okay, so let's see what are the different registers. There are 5 registers: A register, X register, L register, PC, SW. A register is used for the arithmetic operations. Okay, as I have told, if you want to like perform 1 plus 1, for that when you declare 1 will be stored in A register. There will be a register named as A in the memory. 1 will be stored here because it's performing an addition operation. Next is X register, that is used for addressing, means it will store the address values and all. Okay, not exactly, but just remember for now it stores address values. L register, it stores the return address. What I mean is, suppose that this is the int main, and inside that you have called a function add. Okay, this is the add function which you have called, and add function will go to a different part of the memory, and that will be executed, and you will be coming back here. So when you go to the different part of the memory, this address should be stored, right? Because when you return back, this the program should continue from here. So where is this address stored? Is it's stored in L register. Okay, so different types of register, just for the more organized manner. You can also store the address in A register and all, but that will be unorganized. Okay, for the organized purpose you will be using the different registers for different purposes. Okay, and JSub, jump to the subroutine, which I just told you, like add is the subroutine, it jumps to it, and the instruction stores the return address. Okay, this is another instruction, rsub. Rsub means return from the sub address. At that time when you return, what are the address you are returning to, that will be stored in the L register for rsub and jsub. Okay, PC is the program counter, the address of the next instruction. So these are the instructions like add 1, cout 2, like the program you will be writing, right? Hello world program and all. So for that different lines will be there. This first line, second line, third line. So program counter will be this is a program counter. In that, what will be stored here is which address I am current, which address is the next to be executed. That address value will be stored here, so that when this is executed, the computer will come and see in PC what is stored. So based on that, what address is stored, it will go to there and execute the next instruction. Okay. SW is the status world. Status word consists of variety of information including a condition code in the comp instruction. So for now let's not focus much on this, because that will be discussed in depth in the upcoming topics. Okay, so these are the 5 registers which are used for the different type of operations. Okay, so this was the second one. After memory you will have register, and after that the data formats. So let's discuss what is the data format. So data format is nothing but how are the integers stored, how are the characters stored, how are the float values, boolean values, and long values, those things, how it is stored, that is the data format. Okay, so the data format is stored as 24-bit binary number. 24-bit means what? 888, as discussed earlier also. 888 forms what? A word. So integers are stored in this form. Okay, 8 bits here, 8 bits, 8 bits. So total 24 bits binary number it is stored. Okay, so the total number of numbers that can be stored is 0 to 2 power 24 minus 1. Okay, 2 power 24 because there are 24 spaces here, right? 24 bits mean 24 spaces will be there. Total numbers which can be stored is 2 power 24. So minus 1 because it's starting from 0. Okay, so these are the number of integers that can be stored. The next one is negative values are represented as 2's complement. For example, if you have to represent minus 24, if someone asks you represent minus 24 in the binary, okay, so how you will represent is first write 24 here, write the binary value of 24, then take 1's complement. 1's complement means wherever you see 0 put it as 1, wherever you see 1 put it as 0. After that add 1. After you add 1, what the value you get, that is the 2's complement for the negative number given. Okay, so this is how the negative values are represented, this is how the positive values are represented. What about the characters? Characters are stored using 8-bit ASCII code. Like for A there will be an ASCII code, right? Like I think it's 97, so 97 will be converted to binary like 1100 and all. So this will be stored for A. For B it will be a slightly different value, C it will be a slightly different value. So characters are converted to the numbers, numbers are converted to the binary numbers. So the binary numbers are stored in 8-bit ASCII code. There is no floating point in the standard version of SIC. So floating point numbers cannot be stored. Means if I have to store 54.8 in SIC, it cannot be stored. Okay, but in SIC XE it can be stored. That will be discussing in the SIC XE part. Okay, so this was the third part, which is data formats. Next one is the instruction formats. So in the instructions format, what we have, all machine instructions on the standard version of the SIC have the 24-bit format. So 8 is for the opcode, 1 is for the address, index value, and 15 is for the address. See, as I told you, like instruction format, so they will also have like 24 bits in total. Means usually it is 888 divided into 888, but here it is not divided into 888, but here it is 8 and here 1 is reserved, so total left will be 7 here, and 7 plus 8, 15 is taken as another one. So this is for the instructions. Okay, instructions means what? Like add. So add is also an instruction. So when the computer goes here, it will see if it is addition operation, then it will perform the addition operation. Okay, so instructions are also stored in the same registers, and the values what is to be performed, that is also stored in the same registers. Everything is stored in the register itself, whether it be control command, whether it be instructions or the values. Okay, everything is stored in the register itself, but the way it is stored is different. Okay, for the data formats it's 24 bits here, 888, but for the instruction, if you have to store add, it will not be stored just add here, but it will be stored in this format, add and the index value and address where it is to be added. Okay, those things will be specified in the instruction. Just storing add doesn't make any sense, right? So that's what the instruction format is. So let's discuss in depth what is the instruction format actually. Okay, so here you have the opcode. Opcode means object code. Object code means add only, like add, subtract, multiply, and JLT, jump if less than, JEQ, jump if equal to, and many other codes are there. Okay, so these are the codes. What is the operation which is to be performed, that is stored here in the 8-bit. Okay, 8-bit means they will have 8 spaces, 4 here and another 4 here. So each of these will be have a fixed assigned value, like 41, 4C, 04. Okay, so these things will be written in hexadecimal values. Okay, these 4 bits for this one and these 4 bits for this one. Okay, the next 4 things. So each will have an opcode here. Okay, opcodes will be understanding more when we deal with the numerical part. Okay, so for now just understand add is stored here, or subtract or JLT and all those things will be stored here. Operation code, what is to be performed, which instruction is to be performed. X is another value, it indicates the index value, so we will discuss that as well. And address means which location it is stored. Okay, that address value is also specified here. Okay, it will be 15 bits, so it will be stored in the 15 bits format. The number will be stored in binary. Okay, and X is nothing but if you have X as 1, this is the bit which I am specifying. Here the value can be either 0 or 1, right? Because it is 1 bit, either the value can be 0 or 1. 0 means X registers value will be not added. 1 means X registers value will be added. Now see, observe carefully what's happening. There is an X register in the memory. Okay, separately it's present. This is separate, this is separate. In X there is a value like 300. Okay, address is suppose 1000. Okay, so here I can have either 0 or I can have 1, right? So if I have 0 here, what will happen is this will not be considered, only the final value will be 1000. Okay, what I mean is if this value is 0, which means I'll not consider X anything about X, just the final answer will be 1000, means the final address where I am supposed to go. In the other case, if the X value is not 0 but X value is 1 here, means 1 is present in this position, at that time what I should do is I should add what is present in X register in the separate part of the memory, which is 300, along with the address. So that is my final value, 1300. Okay, so this is what's happening in the because of the index value. If the index value is 1, the X register's value is added. If X bit is specified as 0, this will not be added. The final address will be this address itself. Okay, that is the instruction format. The next one is the addressing mode. There are two types of addressing mode, direct and indexed. In direct addressing mode, this is what I meant. Like see here, These are the x is equal to 0 means target address will be equal to the address itself. So if this is written as 0 here, target address will be 1000 only, because this is 1000, right? So that will be taken as 1000 only. But if it is indexed addressing, at that time what will happen? 1 is here, right? 1 means x value what is present here, like suppose 350. So 350 will be added with this value, and that will be my final answer. Because 1 is present here, I should include this one as well. And that's the difference between the direct and indirect addressing. So in addressing modes, there are two types of addressing in SIC: direct and indexed. Okay. The next one is the instruction set. So different type of instructions like LDA, LDX, STA, STX. What does this mean is, LDA means load, LD means what? Load, ST means store. Load means what? If you have a value here, this is the A register, and if you have a value 5, if you write LD 5, LDA 5, LD means load, A means in the A register, 5 means which value. So what is this actually? Hash 5. So what you will do is, you will load 5 into the A register. Store A. Store A means if suppose initially A has something like 100, and you write STA CH. So CH is another variable in the memory. So whatever is stored in A, that will be stored in CH. That is the main difference between LD and ST. So don't worry for now. When you will be solving numericals, you will get to know in a better way what does LD and ST exactly do. Now what is about X here? X is nothing but what is stored in the X register. If you write LDX, it will perform the operation on X register. If you write LDA, it will perform the operation on LDA register. If you write LDS, it will perform the means operation on S register as well. That is just for the which register you are performing the operation. Okay, that is the load and store. And arithmetic operations: add, subtract, multiply, and division. So if you write add word, every time when you write add, subtract, multiply, and division, which register will be used is A register only will be used. Whatever you write here, that will be stored in A register only. Add word means add in A if A has like 0 and word is equal to 1. So what will happen is, if you write add word, automatically A register will be called, and whatever is the value of word, that will be added with the existing value of A. So 1 will be added with 0 and 1 will be stored here. A is equal to A plus word. You did not specify which register you are performing, but still by default it will perform the operation on A register only. Add word could have taken X register also. Some value will be here, it could have added in X register also, but by default it will perform on A only. Okay, all the arithmetic operations are performed on A only. This is how the system is designed. Okay, so that was about the add. Same thing was for the other arithmetic operation as well. Comparison operator. See, comp word. Comp means comparison, word means it is a constant value. Okay, word can be equal to like 7. Now comp means what? It will first take A and see what is stored in A, and it will compare with the word which is given, like the value of the word 7. Which is greater? 8 is greater or 7 is greater? 8 is greater, right? So comp word 7 compares A's content with the word's content and sets the condition code as less than, equal to, or greater than. That's the all the the task of comp operator. It will compare the value present in register A with what value you have specified in the operation. Okay. And conditional jump instructions: JLT, jump if less than, jump if equal to, jump if greater than. Okay, this will be discussing more in the for loop part. Okay, and the same way we have the subroutine linkages also: JSub and RSub. Jump to the subroutine and return from the subroutine. That is nothing but if you have like this, the int main function, and this is the add function. Jump to the subroutine and return from the subroutine. These two operations are for these purposes: jump and return. Okay, and input output. If you have taken any input from the keyboard, at that time the input will be going to the K register. Okay, if you have typed any key here like K, at that time what is the ASCII value of K? That will be stored in register A. Okay, and each key will be each device will be assigned a unique 8-bit code. Okay, so whatever you give as the input from the keyboard, that value will be converted to 8-bit ASCII code, and that will be stored in the register A. That is for the input. For the output, what happens? Whatever the content is present in register A, that will be shown in the screen. Okay, from the 8-bit it will be converted to the character value, and that will be shown in the screen. Okay, so there are three type of input output instructions, which is TD, test device, checks whether the address device is ready to send or receive a byte of data. Okay, test device, what it does is it will like first let's understand what is condition code. See here, it is set accordingly. If it is less than means it's ready, if it's equal to means not ready. Okay, so test device is nothing but you can consider test device as a box. Okay, TD is a box. In that box, either the value can be less than or equal to. Okay, so when you use the test device, at that time what happens is it will check the keyboard. Okay, if the keyboard is properly connected to the computer or not. If it is properly connected, it will store this value here, okay, in TD. If it is not properly connected, it will not store this one, it will store equal to. So based on what value is in TD, we can get to know if the keyboard is ready to take the input and the monitor is ready to display the output or not, based on these two values. Okay, so these two values are set in this way because it is helpful in the for loop part and all. So that's why it is like less than or equal to and all. That will be understanding more in the when you write the SIC programs. Okay, so that was about the TD, and there are two more things like RD. It transfers the byte of data from the input device to the rightmost bit of the register A. RD means read the data, WD means write the data. Okay, so when you call RD, at that time whatever the keyboard input you give, that will be stored in the register A, and when you do WD, whatever is in the register A, that will be displayed into the monitor, which is the output device. Okay, so yeah, that's all about the SIC main things. So to quickly wrap up, what we discussed just now is like memory. So every architecture includes 8 things, so I guess it's 7 actually 7. Okay, so 7 things are there. Memory, it has 24 bytes, it will be stored in this way, 24 bits, and it will be 888. And the registers, there will be 5 registers for different purposes: A, X, L, PC and SW. Data formats, how is the integer stored, how is the character stored. Integer is stored directly in the 8-bit format, character is converted to ASCII code and that is stored here. And instruction format, that is stored in this form, like 8 bits for opcode and 1 is for index value and the 15 bits for the address value. Addressing modes are direct mode and index mode. So direct mode is the direct one and index is the adding of X register value as well. Instruction set and the input output we just discussed now, those are the main things in the SIC. Okay, the same things are in the SIC XE as well, but here we will have the different register formats, and addressing modes will be more like there will be format 1, format 2, format 3, format 4. So few slight differences are there, which we will be discussing in the SIC XE part. Okay, before moving on to the SIC XE architecture, we have discussed some of the SIC programs. If they ask an exam for writing SIC, you have to know how to write, right? So let's discuss how to write the SIC programs. Okay, so the first one is SIC instructions for data movement operations. So data movement means you have some number here, for example. Okay, if you have like 5 will be moved to a register, and after that from the register again it will be moved to the output, okay, or any other variable. So that's the data movement operation. So how to write the SIC instructions? So here the SIC instructions: LDA 5, load in register A, what we have to load 5, and what is 5? I don't know what is 5, so I'll be looking down here. 5 means 5 is a word which is assigned the value of number 5. So if you write word here, that means it is the constant value. Whatever value you assign here, that will be replaced with this one. So it's just like int 5 is equal to 5. Okay, this is what it means. Word means this one. So 5 will be equal to 5. So load in a register A 5. So what will be in register A is 5. Okay, so E will have 5. Then store from register A into alpha. Okay, that means STA. Store from register A into alpha. Alpha is a variable which is created, and here what will be stored is from the register A whatever value it is. So alpha will have 5, right? Then load character char 2. Okay, load character char 2, where it is loaded in register A. So in A, character 2 is loaded, and then store the character A means from the register A in C1. So in C1 what will be stored is what is present in register A, which is 2. Okay, like that it works. And here it is defined like alpha is nothing but reserved word 1, means it is alpha is nothing but, like in C programming we will be doing dynamic memory allocation, right? Like malloc, calloc and all like that. This is malloc here. Malloc reserve 1 byte. 1 byte will be reserved with the name alpha that can be used to store any value. So it is just a variable, okay, with 1 byte here. This is the address means the size which is getting specified here. In the same way, char byte C, and 2 is present here. So wherever I write char 2, the 2 will be specified there. Okay, so that's what it specifies here. 2 is getting added to char 2. C1 RESB means reserve byte, means C1 will reserve 1 byte. 1 byte variable will be C1 without any value as of now, and whenever we perform some value or store some value from the register A, that will be stored in C1. Okay, the same way the other one is the SIC instructions for arithmetic operations. In arithmetic operations, if you have to perform the following operation, like beta is equal to alpha plus increment minus 1 and delta is equal to gamma plus increment minus 1. You have to write the instructions for these two operations. So for that, what is the first thing? Alpha is getting loaded in register A. So whatever the value of alpha is there, that will be loaded. So what is the value of alpha? Alpha is nothing but it's defined as, alpha is the reserve word with the value means the size 1. Okay, alpha is nothing, it's an empty value as of now. So when we assign some value, it will be assigned to alpha. Okay, but as of now, what happened is in A register alpha is stored. Okay, now add increment 1. As I told you earlier also, if you write add here, what will happen? Increment value whatever it is, that will get added in the register A, right? Because by default arithmetic operations perform the operations on register A. So increment whatever the value of increment is, that is getting added with alpha and getting stored in there itself. So what is the value of increment? Let's see if it's defined here. Increment is also a reserved word of 1 byte, so it's not yet defined. So we'll be just adding the whatever the value of increment is in the alpha. So it is alpha plus increment as of now. So what is the next step which is given in the question? It is subtract 1. So we'll sub 1. Sub means it will access whatever is present in the register A. As of now this is present. 1 means 1 is defined as the word which is having the value 1. So subtract 1 means minus 1. Alpha plus increment minus 1, and that will be stored in register A itself. Then store that value in beta. STA means store from A in beta. So beta will get the value of this one. So beta is equal to this value. That's what the question is specified. Beta is equal to alpha increment minus 1. Right, beta is equal to alpha plus increment minus 1. So yeah, 1 is a word, so it is a constant value. Unlike these values, it's a constant value 1. So it's like int 1 is equal to 1. Like that we'll be writing in C program, right? So that is the thing which is specified here. That's how you do for beta. Beta is equal to alpha plus increment minus 1. Same thing goes for delta is equal to gamma plus increment minus 1. Just the names will change. Okay, LDA gamma, in A the gamma is getting stored, and add increment. So increment is getting added. So gamma plus increment. Then minus 1 we will do by using sub 1. So the sub 1 will do minus 1, and the value will be stored from A to delta. So delta will be gamma plus increment minus 1. Okay, that was for the arithmetic operations. Another one, let's see for the string operations how to do. SIC instructions for looping and indexed operations. So to copy a 11 byte character string into another string. So suppose that there is a S1 here which is equal to hello. I have to copy this value in S2. So basic operation what I will be doing here is I will access H, I will be writing H here, then I will access E, I will be writing E, L, L, O. Like that I will be copying from S1 to S2. If you write the C program for loop, we will be having two variables, j is equal to 0, I is equal to 0, S2 of j plus plus is equal to S1 of I, and I will be incrementing until I reaches the end. Okay, and at the end we will be adding S2 of j. Okay, so LD of x is equal to 0 will be first initial. This is the SIC instructions how to write. LDX is equal to 0, load into X register. What we have to load? 0. So let's see what is 0. 0 is a word which has the value 0. So it is a little value 0 here. Okay, another one 11 word is 11. Okay, and so register X has the value 0. So this is the X value 0. Loop load character string 1 X. X value is what? 0. So string 1 is what? String 1 is defined as, it's a byte of characters hello world. So this is the string 1 we have, and what is getting specified here is str1 of x. At the x position, what is the value of str1? That should be loaded into the register A. Okay, load ch str1's x value. X value is 0 initially, so 0th index of str1's value will be loaded in register A. So in register A, what will be loaded is H. So H will be loaded in register A. After we have loaded H in register A, what we are doing? we are coming to the next operation, which is store the character ch, which is the present in A. So that should be stored in str2. And at which location it should be stored? It should be stored in xth location. Xth location is nothing but 0th location of str2. So what we have is A is here, it has the value h here, and store the character ch from the A value to str2. str2 is this one, so str2 is this one, and we have the 0th location here, and we have to store the h value here. So h value will be stored in this location. Okay, xth location, h value will be stored. That's what the specific means. That's what the command specifies. So store the character from the location register A to str2 at the xth location. Then tix means increment and compare. Tix means increment and compare. Then 11 is written here. 11 is substituted as 11. Okay, what does tix means? Tix means increment the x value. Increment the x value. X value is 0, 0 will become 1. 1 compare with 11. If you compare 1 with 11, is it equal to 11 or less than 11? It is less than 11, right? 1 is less than 11. So what I will do, I will come to the next one. 1 is less than 11. I have the value of tix as less than. Then jump if less than. Jump if less than to loop. Less than what? Less than this operation. So this operation is less than. It's correct. So I have to jump to loop. So loop means I will be starting from here again. So this is loop. Wherever I specify loop here and I write GLT loop, it will come back here and again do the same operation. Now x value is not 0, it is 1. So what will happen? X value is 1. str1's 1th location, that will be stored in LDCH, means register A. 1th location of str1 is nothing but E. E will be stored in register A. Okay, E is stored in register A. Then the next operation, which is STCH, store from the register A into str2's xth location, which is the first location. So str2, as you had stored earlier, str2 was first having h here. Then in the first location, what will be stored? E. Then again I will come here, tix 11. Tix means increment the x value. X will become 2 and it will be compared with 11. It is less than. Jump if less than to loop. Again it will go to loop like that till how much it will happen? Till 11 times. Why 11 I have chosen? Because it is the length of the string, right? This is the 11th word here, right? So that's why until all the string is copied, I will be doing the same operation. After that is done, JLT loop will fail and it will come to the next part. Okay, so we'll have in str2 hello world, which was the content of str1. That's why you copy the string from str1 to str2. If you do not understand, you can always replay back and watch the explanation again. Okay, so that was about the string operation. Moving on, we have the array operations. So here what we have is program to add 2 arrays of 100 words each and store it in another array. Each word is 3 bytes. 100 word means 3 into 100 means 300 bytes. Okay, 100 words are there, each word is 3 bytes, so it will be 300 bytes. Okay, so basically we have 2 arrays here. If I give you the visual representation of what's happening, A is here, B is here, and this is the resultant string. Okay, let's take it as G. Each has how much words? 100 words. Okay, so here 100 words are there and here also 100 words are there, and here we have to store the result. So what we will do first, we will access this location, we will add it with this location, and that answer will be storing in G. So basically we will be taking this value and storing in register A. Okay, in register A we will be storing this value, we will be adding this value to the register A, and whatever is in the register A's result, that will be storing in the first location. Then we will be accessing this location and storing these values, then this location and these values, and so on. Okay, like that we will do till the 100th word. That's what's happening here. We are starting from here, add loop. So this is the name which is specified here, add loop, and we have loaded in the register X index value. Index is what? Initially it is 0, so X value will be 0. X register will have 0 in it. Okay, then load in A register what? Alpha at the Xth position. Alpha is nothing but alpha is the first array. Okay, first array name is alpha, second array name is beta, and third array name is gamma. Okay, so alpha's 0th location value, that is getting added in register A. Okay, and then add beta and Xth location's beta value to register A. So beta's Xth value will be taken, and that is added in stored in register A. So A register has what? The value alpha's Xth location, which is 0th location, and beta's 0th location. That value is stored in A. and this should be stored where? It should be stored in the resultant array's 0th location. Here it should be stored. So that's what we are doing here. Store from the register A to gamma's xth value. Xth value is 0, so gamma's 0 value will have the addition of A's first value plus B's first value, right? Then what we are doing, we have done this one, then we have to increment the x value. We can't just write x plus is equal to 1 like in C++. We have to do the arithmetic operation using the means the registers. Okay, so after we have done this one, we have to increment the x value for the next operation. LDA. LDA means load into the register A what? Index value. Index is 0, so A will have initially 0. Now A has 0. Add 3. 3 is what? It is a word which is written here, right? See here, 3 is a word, so 3's value is the literal value 3. Okay, so add 3 means whatever is present in the register A, that will be added with 3, so A will have 3 now. So A register has 3, and then we are storing that A's value in the index. So index will become how much? 3, right? Because A has 3, that will be stored as 3. Now index value is 3. We are comparing if 3 is less than 300, then K300. If comp K300, what is K300? K300 is nothing but it's also a word which is having the literal value 300. So 300 and 3 is getting compared. Is 3 less than 300? Yes. So this will be stored. When this is stored, less than is stored. So what we are doing? Jump if less than to add loop. If 3 is less than 300 means all the words are not yet over, only just one word is over. So if it is less than means the value I have got here is less than, so jump if less than to where? Add loop means repeat the loop. Now the index value is 3. So if the index value is 3, it will access the next word. So first word is done, okay, that is stored in gamma, then the next word will be accessed and the loop repeats. This will be added with this one, it will be stored in register A. Okay, in A it will be stored, and that A's value will be stored here. Then again the index value of this one will be stored in A. 3 will be added, so it will be 6. 6 will be stored in index value, and then we will be comparing the index value 6 with 300. It is less than, again it will jump here. If it is less than, so again we will be starting from here with the index value 6. Okay, means the second word will be accessed. Like that it goes on till it becomes equal to 300. That means all the words are over, so it will not jump again to the next loop, and it will do the next operation. Till then we will have in gamma all the sum of the first two arrays in respective index locations. Okay, that's how do you perform the array operations. Fine. And moving on, we have the fifth one, which is the last one, which is to read 1 byte of data from the input device and copy to the output device. Okay, so what we are doing, we have the keyboard here. Okay, suppose that there is a keyboard here, and when you open notepad in your computer system, at that time you will be seeing a cursor here, right? If you type A, it will be showing A here. But what's internally happening? Internally what's happening is A is fetched, that is stored in another register, and from that register it is getting displayed here. Now your task is to write the code for how to get this value and store in which register and how to display it. That code you have to write, okay, in the assembly language. So let's see how to write the code for it. Okay, so here is a loop here. In loop means how many ever values we enter from the keyboard, that should be keep on getting the input, right, repeatedly. So for each character, one time this loop will run, for the next character next time loop will run, and so on. Okay, so what's actually happening here is, first we are doing td in dev. Okay, td in dev means what? Test device. In dev means input device. Test the input device. Test if the input device is ready or not. If it is ready, it will give the less than sign. If it is not ready, it will give the equal to sign. Okay, these two are the test device means values that I have discussed in the theory of this means SIC, right? The test device, input output operation, at that time I discussed, it can be either less than value, conditional code, or it can be equal to value. If it is less than value means it's ready. Always remember, if less than means it's ready, if equal to means not ready. Okay, so based on this we will get either this one or this one. Now if it's ready, at that time what I will do, I will go to the next operation, right? If it's equal to means it's not ready. If it's not ready, again I should test for the device. I should keep on testing until it becomes equal, right? So that's what we are doing here, JEQ. So JEQ means jump if equal to. What I told you, if it is less than means it's ready, if equal to means it's not ready. Jump if equal to. If it's not ready, then jump to in loop, means again keep on testing until it becomes ready. It becomes ready means this will not run and this will come here. So until it's not ready, we'll keep on testing for the input device. Okay, that's what's happening here. Then RD input device. RD means read. read the input device value. Once ready, read the byte into the register A. Whatever key you type, that will be stored in the register A, and that value will be stored here, and from there it will be stored from the store the character present in register A to data. Data is a variable which will store the value what is present in register A. Register A, suppose X is present, that will be stored from X, the register A to data. Data is another variable and that has the value X here. Okay, so that's how we read the input from the keyboard and store it into the memory. Okay, so now the next one is the output, right? For the output also we will be doing the same thing. Out loop is the word which is the loop word. If it is equal to, means it's not ready. At that time we will keep on testing until it is ready for showing the output, and TD is the thing which tests the output device. And LDCH means load from the load to the register A the character which is stored in data. So in data I had stored X here, so that will be stored loaded in register A. So this will be loaded in register A, and write to the output device. Whatever WD means write from the register A whatever is stored here to the output device. Output device means the monitor. The monitor, whatever is present here, which is X here, X will be displayed in the monitor. Okay, so instead of X and all, what is specified here is indev is specified as F1. So F1 is getting pressed in the keyboard, that is getting stored in the data, and from the data what is getting displayed is OS. Okay, because that's what they are specified in the question. Right, like from 1 byte from the input device, input is not specified but output is specified OS. Okay, and data is a reserved byte of size 1. Okay, so here is another one. If you want, you can skip this one as well, but if you watch this as well, it will be helpful for you. Okay, so here jsub is nothing but the subroutine. You can call it as a function, like how we write the functions in C++ and all. That's the same thing here. Subroutine to call a 100 byte record from an input device into the memory. Read a 100 byte record. So let's break this down. Read a what? 100 byte record. Okay, 100 byte record from where? From an input device to where? Into the memory. 4 parts are here. So what we are doing is a reading operation of 100 byte record. So there is a 100 byte record in the memory from the input device. So there is not in the memory, but in the input device we are going to give a 100 byte record, and that will be read into the memory. That's what's happening here. So jsub means jump to the subroutine. Jump to the subroutine. Subroutine's name is read. So it will search where is read present here in the labels part. So wherever is read present here, that is a subroutine. Okay, so it will start from here and it will jump to this part, and this will be executed now. So until it returns, it will execute. When it will return, when it encounters rsub. Okay, so until it encounters does not encounter rsub, it will be present here itself. It will be executing this loop here. So what's happening in this program? Load into the X register 0. 0 is specified as 0 here. 0 is a word specified as 0, and K100 is a word specifying 100. Record is a reserved byte of space 100. Indev is a byte which has the value character F1. Okay, so we are starting from here. Load into the X, so X register will have 0 here, and loop TD in device means until the input device is ready, that we had already discussed. It will keep on asking, and when it's ready it will come here. And RD means read the input device. Read 1 byte from the input device. What does input device specify is F1. So F1 will be read, and that will be stored into the A register. That will be stored into the A register at the from the CH. What is CH is the record at the 0th address. So what is present in register A, that will be stored in record at the X position. So what is stored in register A? Register A, I have read the value of indef, which is F1, that will be stored in register A. So F1 is stored here, and that will be stored, means it is present in this register. STCH means store this value into record at the Xth position. Record is nothing but it is a 100 byte array, right? Because I had shown you what does record mean. So it was a reserved byte 100. So in the X location, X value is 0. So 0th location, what will be stored is F1. F1 will be stored here. Then what will be compared is TIX. TIX means X value will be incremented, X will become 1. That will be compared with K100. K100 word is a word which has the value 100. 1 is compared with 100. If it is less than, means the value I get answer as less than, then go to R loop. Again go here and fetch the next word, and again store it in the A register, and from A register store it in record at the X position. X is 1, so first position, so then second position, third position, fourth position, till 100th position it will go. When it's 100th position, this will not run, this will be failing, this condition will be failing, and it will return from the subroutine. Okay, that's how you use the subroutines also in the assembler functions. So these were the 6 types. If you saw all the 6 types, it's very good for you. It will be helpful in writing the object program codes. Okay, means the conversion of the code from SIC and all those things are there. Okay, so if you are thorough with this one, you can move to the next part. Okay, in the next part we will be going with the SIC XE architecture, and then we'll be solving the numericals for SIC XE, means writing the programs like how we wrote for SIC, right? SIC XE also it's the same thing, but slight differences are there. So let's discuss what are the differences. So this is the SIC XE machine architecture. SIC XE means a simple instructional computer. SIC is same as this one with extra equipments. Okay, means some extra things are there which makes it more efficient than the previous one. Okay, so let's discuss what are the different things present in SIC XE. So in SIC XE, these things are same: memory, register, data formats, instruction format, addressing mode, instruction set, and input output device. So these things are same, but inside these things what are they, that differs. Okay, so let's discuss the first one, which is memory. In memory, there is the same thing. It consists of 8-bit bytes. 3 consecutive bytes form 24-bit words. All addresses are byte addresses. Just the difference is the total of 1 MB. In the previous one it was 32768, right, which is 2 power 15, but here it's means more memory, which is 2 power 20 bytes. Okay, that's the only difference between SIC and SIC XE in the memory. Okay, so there is more memory in SIC XE. Next one is the registers. So in registers we have 9 registers. In the previous one you just had 5 registers. If you remember, it was A, L, X, S, W and PC, right? 5 registers were there. Now along with this one, 4 more registers will come: B, S, T and I guess F. Okay, these 4 registers will come extra to this one. Okay, so each register's length is same as previous one, and here we have the floating point also. Okay, so these are the 9 registers. These were the previous registers as well, like it was present in the previous one. A was present, X was also present, L was also present, B, S, T, F. These are the 4 registers which are new. PC and SW was in the previous case as well. Okay, so one more thing, B means base register, F means floating point accumulator. So to store the floating point, we will be using this register. In the previous case, if you remember, floating point was not available in SIC, but in SIC XE it is available. Okay, base register for use for addressing. These are the 2 general registers used for any purpose. Like suppose if you want to add 2 numbers. Okay, one way of adding 2 numbers is you can write LDA 5, then add 6. You can do like this, right? So what will happen is 5 will be loaded in register A first, then 6 will be added to 5, so 11 will be stored in register A. The other way is, what you can do is you can use 2 registers, because since we have S and T as a general working register, no special use, so you can use this register for any operation. Okay, like for example, if I use for arithmetic operations, I'll write LDA and there I'll store 5, then LDS I can store 6. So in the A register I'll have 5, and in the S register I'll have 6. So then what I will do, add A comma S. Well, if I do A comma S, what will happen? S content will be added in A and stored in A itself. So 6 will be added in 5 and stored in this one itself. So the answer in register A will be 11. Okay, that's what the general registers are used for. Any operation you can use, you can also use for addressing and the other operations. Okay, so these are the 9 registers which are present in SIC XE. Okay, then we have the data formats. In data formats, we like the integers stored as the previous one, same 24-bit for the positive one, and the negative values are represented by 2's complement, same things. Just the difference is that in the previous one float value was not accepted, but here float value will also be accepted. So for float value there are 3 things here. It is total of 48 bits, I guess. So here the first is S, and exponent and fraction. So S is nothing but the sign value, means if it is positive or negative fraction, and exponent is nothing but, like if I give an example you will understand. So suppose that it is 4.89. okay, 4.89, 4 is represented in binary as 100, point is there, then 89. How to represent 0.89 in binary? In binary what we will do is we will take 0.89 multiply by 2. What answer we get? If we like take the, if suppose that 89 into 2 is, I guess, 178, I guess 1.78, I'm not sure. So if you take 1.78, 1 is present here, right? So So that you will take as 1. You will write 1 here and subtract 1, so it will become 0.78. Just consider the fraction part. Again multiply by 2, consider the fraction part. Again multiply by 2, consider the fraction part. So if you reach here 0.12, if you multiply by 2, you will get 0.24. The fraction part is 0.24, but the other part is 0. So since you got 0 after multiplying this by 2, let's take it as 0, right? So what I mean is 0.89 into 1.78. What you got here? 1. You wrote here 1, but you have 0.12 here. If you multiply by 2, you will get 0.24. What you got here? 0. What you wrote here? 0. Like that you will keep on writing, means for 10 or 12 points. After that you will get a binary number. That binary number will be written here in this form. Now what your task is? It is 100 point this one. This represents 89 and this represents 4. Okay. Now you can write it like this: 0 point, this one all will be shifted here, and you can write into 2 power 3 at the last, right? That doesn't make any difference, right? If you have 10.1 or 0.101 into 2 power 2, both are the same things. Like for example, if it's in the decimal, it will be 10 square, right, into 100. 0.101 into 100 and 10.1 is same values, right? The same thing goes for binary as well. Instead of 10 we have 2 because it's binary, so 2 power 3, and what value you get here, that's the value of exponent, and this is the value for the fraction. Exponent is 3, so in the representation of this one, what you will write is s as positive, so you'll write 0 or 1. I'm not sure if it's positive, it's 0 or 1, I'm not sure, but any either of this you will write here s, and exponent value you will write 3, which is 0, 1, 1, and fraction part, what value you got here, this is the fraction part, this you will be writing in the fraction part. Okay, this binary combination. So that's how you represent the fractions in the SIC XE. Okay. So that was for the fractions, and I have discussed the integer as well. The character also will be same only as the previous one. Okay, like the ASCII values will be converted and it will be stored. Coming to the instructions format, as I told you, like we have 4 formats. In the previous instruction format, if you remember, what were the 2 instruction format? It was not 2 instruction format, it was like opcode here, it was index value here, and here we had the address value, right? It was 15 bits here, it was 1, and it was 8. But here we will have 4 formats. Okay, 4 formats for different purposes. That purposes actual use you will be understanding when you will be solving the numericals of opcode. Okay, so until then, just remember these things. Just watch it once. Even if you don't understand, don't worry. Just watch it once. That's more important. Okay, because if you skip, it will be very, very hard. Okay. So there are 2 possible options: either use the same form of relative addressing, extend the address to field to 20 bits. So since XE is a bit more memory, so we'll be extending the bits. Instead of 12 bits, we'll be having 20 bits. Okay. So if it is E is equal to 0, E is equal to 1, this I'll be discussing now what is format 3, format 4. But before format 3 and format 4, we need to know what is format 1. Okay, format 1 means 1 byte. 1 byte means only opcode will be stored. This is the instruction set, only opcode will be stored. In the previous one, what we had in the SIC, we had opcode here, and we had the index value x here, and we had the address here, right? So in the format 1 of SIC XE, we'll just have opcode. So opcode is of 8 bits. It can specify any value like r sub. Okay, it's just an instruction for like exit the code, start the code, or go to the subroutine, return from the subroutine. This is known as return from the subroutine. Okay. So what is the opcode for it? Means the numerical form, means hexadecimal form of this word, equivalent of this word, that will be stored in the instruction format. These are the fixed values. Okay, for r sub it is 4c, for LDA, LDX and all, they are the fixed values. Okay, that is stored in the system, designed in the system itself. You just have to look up for what instruction we need to perform. For that, what hexadecimal value is there, which is known as opcode. That opcode will be stored in this one, format 1. Okay, so it is required 8 bits. Why? Because 2 things are present here, 4 and c. 4 is represented as 0100, C is represented as 1100. So 4C is the object code, and that will be stored here. That is for the format 1. If you just have to specify an instruction, okay, like exit, start, or check, like that, one word instruction is there. Only if one word is there in your instruction, use the format 1. Okay. If there are 2 things like you have to compare 2 values or add 2 values, for those things it's not just sufficient that you use instruction. Like suppose if I just say add, you'll obviously ask me add what. If I just say compare, you'll obviously ask me compare what. So to compare what, I need 2 more values. Add means I need 2 values to add, right? For compare also I need 2 values to compare. So for that 2 values extra space is needed. For that format 2 is needed. Okay, So format 2 will have 2 bytes. This is byte 1, this is byte 2. Byte 2 is divided into 2 parts, for one for the operand 1 and for the operand 2. Okay, like compare a comma s. So a's value will be stored here, s value will be stored here. A means what? A's register, whatever value stored in a's register. S register, whatever value stored, that will be stored here, and that will be compared. And what I have to do, either I can add, compare, subtract, multiply, everything I can do, right? What is the exact instruction, that will be specified here. Here I will specify if it is add operation, add these two values, subtract these two values, multiply, divide, compare, whatever I want to do. Okay, so those instruction will be specified here, and the operands on which the instruction is to be performed, that will be specified here. Okay, so for an example, the opcode for compare is equal to A0. A0 is a inbuilt value, which is the fixed value. A0 means the computer will understand if you write A0 here, it means compare operation. Now compare on what two values? R1 and R2. R1 has 0 here and R2 has 4 here. Okay, so 0 and 4 will be compared. Okay, so based on that the answer will be specified. Those things we will discuss later. Okay, where the answer will be stored and all. For now, just remember this is how the instruction is specified and the operands are specified. Okay, moving on, we have the format 3 and format 4. Format 3 and 4, it's a big one because we are performing more operations, and the most used are format 3 and format 2. Okay, format 3 and 2 are most used in the opcode writing of the code and the assembly translation. So observe carefully and remember this very well. Okay, so what's happening here? Firstly, how many bits are there? 6 bits. 6 plus 6 12, 12 plus 12 24, total 24 bits. This is there. Okay, 24 bits register is there. Now in the first 6 bits opcode is there. In the first 6 bit opcode is there. Opcode means add, subtract and all those hexadecimal values code that is stored here. What operation is to be performed, that instruction is stored here. Next what we have is 6 flags are here. Flags you know, right? So the 6 flags are here. I will be discussing this in a few moments. Before that, let's see what is displacement. Displacement means address. Address means where I have to perform the operation. If it is add operation, where I have to perform the add operation, that will be specified here. If I show you an example here, this is the value 003. 003 is this address value. On 003 location, what is present, there I have to perform this operation. 00 is the opcode for LDA. Load into register A. Okay, listen carefully. Load into register A the value which is present at this location. That's what I am specifying here. At this location, what is stored? 3. So 3 will be loaded in register A. Okay, even if you don't understand, it's okay, because when we discuss the more problems, there will have multiple examples. Okay, sufficient examples for the like you will be easily able to understand. Okay, so for now, just keep in mind there are 3 parts specified here. One is the opcode, another one is the flags part, and another one is the address or whatever value it is. Okay, so let's see what are the middle part. NIX BPE. Remember these 6 letters. NIX BPE. NIX BPE. Okay, now it's upon you how you remember, but you have to remember. Okay, so N means what? Indirect bit. I means immediate bit. X means index bit. B means base bit. P means PC relative bit. E means extended bit. Now I will be discussing in detail what does each of these terms mean. Okay, indirect bit means suppose that we have 2 registers here. A has the value 10 and there is another register with the address 10 and it has the value 7. So if I have to fetch 7, at that time I will be making this bit as 1. So if I am not using that type of addressing mode, I will be specifying that bit as 0. Means at each location in this one, either it will be 0 or 1. 0 means that that mode is not used. 1 means that mode is used. So what will happen here is indirect bit. Indirect bit means if I specify A, at A location what is stored, that location what is stored, that value I need. Indirect bit. Direct means direct what is value stored, that I will use. Indirect means what value is stored, at that value what is stored is used. Okay. Immediate bit means I will be using that same value. Means if I specify immediate bit as so you will understand it in a better way here. So hash is used for immediate bit. Okay, immediate bit means whatever value I specify, that will be loaded. Okay, and the next one is X. X means indexed bit. So what will happen is this value plus the index value. Index value means in X register what is stored, like 300 is stored, as discussed earlier also. Remember, this value will be added with 300 and that will be the target address. Okay. B means base relative. Base relative means this plus base value. PC relative means this plus PC value. E means if E is 0 it is third format 3, if E is 1 means it is format 4. That is getting specified here. Now what difference that 0 and 1 make, that we will discuss later. Before that you need to understand these terms. Okay, so we will be solving some examples. In that it will be very clear for you what does each term mean, how to use each term in the problems. Okay, so in a few moments I will be solving an example. I will be discussing different types of addressing modes, wherein means these bits will be on and off, means in a different combinations. Okay, so let's keep that for later part and let's discuss what is the format 4. The only difference which happens in format 4 is this is 12 here, right? 12 for the address, that is getting incremented with 20. That's the only difference in format 3 and format 4. One more difference, if it is plus here in opcode, plus J sub RD record. RD record is the address value will be stored here, J sub is the opcode which will be stored here, plus specifies it's a format 4. Okay. So as I have already told you, like opcode for each of the instructions like add, subtract, multiply, J sub and all those things, the opcodes are constant, means those are fixed in the system. So for each of these word like J sub you find here, for that opcode is fixed. Okay, like for J sub it is 48. So 48, how do I represent? 48 I can represent by using like what is for 4, the binary value is I will be doing in this way. Okay, like not 48 the whole value 48 number will be converted to binary, but 4 will be converted to binary, then 8 will be converted to binary. That's how hexadecimal works, right? So 4 the value is 0100 and 8 value is 1000. Okay, now how many bits are there? 8 bits are there, right? But 8 bits can't be stored in 6 bits here. Opcode I have to store this whole value. So what I will do, I will just store the first 6 bits, the rest 2 will be discarded. So what is the value? 0100 and 10. That's all will be stored. So here we have 0100 and 10. Okay, that's all what will be stored here. That was for the opcode. Opcode how is specified? By using this one J sub. So J sub value is 48. I know 48 is 0100 and 1000. By that I got like it is just a 6-bit storage. So I will be just storing 010010. This will be specified by the operation. If it is is it indirect operation? No, it's not. Is it immediate operation? By seeing this only you should understand. If it is not indirect, not immediate also, both will be set as 1 or both will be set as 0. That's your choice. Okay. Is it indexed value? Anywhere index you can see? No. Is it base relative? No. PC relative? No. Is it fourth format? Yes, it's fourth format because plus is here, so E will be made as 1. After E is made as 1, we'll be using the 20 bits here divided as 4 bits, 4 bits, 4 bits, 4 bits, 4 bits. Okay, like that 20 bits will be in total. So after that is done, what is the address of this one? Address of this one will also be given in the question, so you can easily see from that it is 1036. So it is 5 sections, so I'll have 01036. 0 will be stored here, 0000, 1 will be stored here, 0001, 0 will be stored here, 3 will be stored here, 6 will be stored here. So the address will be 01036, and from here what will happen is 4 bits will be choosing at once. So 0100 is 4, 1011, okay, it is coming to other section, but that doesn't matter, you have to choose it in that way only, 4 bits at a time. So 1011 is B, 0001 is 1, and this 4 bits, 4 bits, 4 bits, 4 bits and 4 bits. So what value you get here, that's your object code. Okay, like that you will have to generate the object code for all the means the whole program. So this is SIC instruction. See, this is the main thing which you need to learn from this module. In this module you will be given with these instructions, and the opcode will be given to you, and the address will be given to you. By using the opcode and the address, you have to write this one. After you write this one, you will be able to generate the object code. Object code will be written here, like that for all of the lines you have to do. Okay, so we'll be looking in detail how to do that, so don't worry about that now. Just get to know the basic. Even if you got 10% of what I told, it's sufficient for you. Okay, so that was about the format 4. Even I know many things will be confusing for you right now, but that doesn't matter. We will be discussing more examples. It will be clear for you hopefully at the later stage. Okay, so for now it's just this much only. We'll be discussing some examples. by using which we will be understanding the different type of addressing modes, what I told, right, like NIX, BP and all, like switching on and off different type of combinations. What is the answer we are getting, that we will be discussing now. Okay, so these are the different types of addressing modes that can be in the program. B is equal to 1, P is equal to 0, B is equal to 0, P is equal to 1, and so these are the different combinations, like B value and P values, it can be 0 or 1, and along with B and P values you have the other values also, like N, I and X values. So those will be also in different formats. So let's see what are the different addressing modes. Total there are 8 addressing modes, so let's see one by one. Okay, so first one is base relative. B is equal to 1. B means what? Base. Okay, so base relative. P is equal to 0 means it is not PC relative. Either B will be 1 or P will be 1. Both can't be 1. Okay, both can be 0 but both can't be 1. Okay, so if it is base relative, what will be the target address? Target address means, see, in the normal case the address will be taken as this one only. But if it is in the like if I show you the previous example, in the previous example like SIC, okay, remember SIC, in SIC this was the format, OP code was here, then we had X value here, then we had the address here, right, address. So if it was the normal operation, at that time the address value was taken as target address, whatever is stored here that was a target address. But if X value was 1 at that time, whatever the value was stored in the register A, that was getting added with this register value, and that was the final target address. So that was the 2 operations in SIC, but here we have 8 operations, right, because there are different bits here, like many combinations are possible. So those are the things which I had to tell. So in the target address, what will happen, B value in the base register, B register we have, right, in SIC XE also, whatever value is there, like 300 if it is in base register, that will be added with the displacement value. Displacement is nothing but the address, normal address. Okay, this is the displacement only. So that will be added and that will be the target address. If it is PC relative, what is in the PC register, program counter register, that value will be added with the displacement and that will be the target address. Okay, direct addressing, B is equal to 0, P is equal to 0, so that will be just the displacement, means directly it is target address only, nothing added or subtracted. Okay, now base relative as well as indexed. So B is equal to 1 and X is equal to 1, that is base relative and indexed. So B as well as X, so what is present in B register plus X register plus the displacement address, that 3 will be added up, that is the target address. If it is B is equal to 0 but P and X are 1, that is program relative index addressing. Here P and X values are added with the displacement, that is the target address. If it is immediate addressing, I will be 1 and N is equal to 0. I is equal to 1 means immediate addressing. Okay, so target address itself is used is the operand value, no memory reference is performed. Okay, operand value is used means what is the immediate addressing, the constant value which is specified, that value itself will be taken, like LDA hash 3. So 3 will be taken as the target address. Okay, means the value. And indirect addressing means N is equal to 1, T is the displacement value, in this case also the displacement value will be taken, I is equal to 0, N is equal to 0, or both is 1, both 0 both 1, that is also taken as location of operand. So all of these will be discussing in by using an example in the upcoming slide. Okay, so before that, here are some the special symbols indication. Hash means immediate address, at means indirect address, plus means format 4, star means the current value of PC, C means character string, OPMX means X denotes the index register, base means base register, and in immediate addressing, the target value is itself used as the operand. Indirect addressing, the value is fetched. See, what does indirect addressing means? Again, I am telling, like A is 10 here and 10 is stored as 7 here. So A's value will be fetched, and that in that what value is stored, that will be fetched. Okay, that is indirect addressing. N is equal to 1 in that case. So this was the basic, the theoretical part of the addressing modes. So let's discuss practically by using an example. Coming to the examples of SIC XE instructions, here we have 5 examples. So we'll be discussing actually 6 examples we have. So we'll be discussing each one by one. So what we are trying to do is, like we are trying to set here different bits, like N here and I here, and rest are 0 here, P is 1 here, P is 0 here. So we are trying different combinations and seeing how to actually calculate the target address. Okay, so in the first example we have the number 032600. Okay, how is this number stored? That we'll be discussing later. Okay, or we can just discuss now itself, like how is this number coming, like opcode is given here, and n value till e value, and the displacement address also is given to us. So take 3 bits at a time. 0, then here it will be sorry, not 3 bits, 4 bits, so it is 0 here. 0 0 1 1, what is 0 0 1 1? It is 3. Then 0 0 0 1 0, that is 2. Then 0 1 1 0 6, 0 0 it's 0, 0 0 it is 0. So here we got 3 2 0 3 2 6 0 0. In that way we have written this code here. Okay, so if they give you like this, you have to write these things in the following order: 6 bits, first 6 bits here, then the next 6 bits here, then 12 bits here, like that you have to write. Okay, so observing this carefully, n is 1 here, I is 1. This is simple addressing, because if n and I both are 1, and but it is p is also 1, so it is PC relative. So what will be the target address? In PC relative, the target address will be equal to PC plus displacement, right? So PC will be added and the displacement will be added. What is stored in PC is given here. In PC 3000 is stored, so 3000, displacement value is 600, 600. So 3000 plus 600, 3600. That is the target address. Okay. In the same way, the second one, 03C 300. Here what is given? N is 1, I is 1, X is 1, B is 1. So B is 1 means it's base relative. Also X is 1 means it's indexed, right? So we'll be adding the base value plus index value plus displacement value. All the values are given here. Base value and the index value is given 6090, and the displacement value is this one, which is nothing but 300. So 300 plus 90 plus 6000, which is 6390. Okay. Then we have third one. Here we have n is equal to 1 and p is equal to 1. N is equal to 1 means it's indirect, right? So indirect means what will be the formula is indirect plus programmability, that is nothing but PC plus displacement. See, in indirect what happens is target address calculation will be same. If it is PC, it will be PC plus displacement, but what value we get, that matters. Okay, like we got 3030. So for now, just keep in mind how to calculate the target address. Then in the next in the next step we will be discussing what do this target address mean. Okay, so we got here this is discussed, and for this one it is I is 1, immediate address. So in immediate address what happens is the value of the target, means displacement will be the final value. So immediate address, TA is used as the operand value. Okay, how we got immediate address? Because I's value is 1 here, rest all is 0. Okay, so that is the immediate address. The next one, here we have the last 2 bits as 1. So let's see what are the last 2 bits. It's P and E. E is 1 means it's format 4, and P is 1 means it's PC relative. So in PC relative we will be having these things. 3000 in PC, the value is given up 3000, and 600 is from the displacement, so it is 3600. See, format 3 and format 4 does not differ in this one, it is same, but what happens is like we will be having the different memory address. Okay, not memory address, but we will be having the displacement address bits as 20. That's the only difference. Okay, so here what we have, the last one, we have n is equal to 1, I is equal to 1, as well as E is equal to 1, and here is the value. So this value, if you write here, it is means the bit value. If you write, what answer we get is C303. This is 0, this is C, this is 3, this is 0, this is 3, 0 C303. Also it is the simple addressing, so the answer will also be the same, C303. Okay, so simple addressing, the location of the operand will be there. Now as we have got these things, now we will be discussing what do this each target address mean. So target address is nothing but in the memory we will be having addresses, right? Address 1 2 3, like that. These values are the same values, like 3600, 6390, and so on. Okay, so for the first one, 3600, we will be seeing the memory. So you can open the PDF in a different device and follow with me. So what's happening here is the value is 3030, 3600. These are the values which are given to us, and in 3600 in the memory by default it is stored as 10300. So that value is used here. Okay, so what will be loaded into the register A is this value. What will be the target address? In the target address, what value is there, that will be stored here. This is also the next one. This is also the base relative. So just what will be stored here, that will be means copied to here. So 6390, what is stored is 0030 C303, that will be stored here. Okay, but this one is the indirect addressing. Indirect addressing means in this address what is stored, in that address what is stored, that value will be taking. For example, in 3030 what you can see is the value which is stored is 3600. Then we will go to 3600, and here what is stored, that answer we will be taking. Okay, means 10 and 3000. Okay, so the next one is pretty simple one, 30. So the answer will only be 30. So here 30 is not mentioned, so the answer will only be 30 because it's direct addressing. Okay, And 3600, what value stored, we've already seen it is 103000, and here we have C303. In that, what value is stored? In C303, what value stored is 03030. So that value will be stored in the register A. Okay, so this is how this was the simple example of how the addressing works in different modes. And let's move on to the next topic, which is the programs in SIC. Okay. So till now we have discussed the first 5 things, which is memory, registers, and the remaining things, which are data format, instruction format, and addressing modes. So the next one is the instruction set. Okay, in instruction set there are different types of load and store instructions. LDA, LDX, everything will be same as in the SIC, and integer and floating arithmetic. So here we have the floating point as well, so we have written F here, and the moving the registers, that command is RMO. We have ADDRs as UBR, MULR, division R. So we'll be discussing the uses of register in the upcoming numerical. And we have the special supervisor call is provided. Executing this instruction generates an interrupt that can be used for communication with the operating system. Okay, and the comparison operators comp R, comp F, conditional jump JLT, JEQ, GT, subroutine linkages J sub and R sub, same as the previous one. Input and output is also the same. The transfer of 1 byte from the input device to the register A, or from the register A to the output device, and each device has a unique ID. The test device sends like less than means ready, and is equal to means not ready, and it does 2 operations. RD is write data, read data, and WD is write data. Okay, so these were the basic like the discussing right memory, registers and all. So for SIC architecture, these are the things which you need to explain. Okay, then we have the comparison between SIC and SIC XE. Okay, so first is the specification is the memory. Here it is 3 bytes, it is same. Here it is 32768 bytes, but here it is 1 MB. Actually it is 1 MB. I have written 32768. You can correct it, it's 1 MB. Okay, and the total registers here are 5. Here the total registers are 9, and here the addressing format is just this one: opcode with 8 bits and X with 1 bit, and address with 15 bits. Here 4 instruction formats: format 1, 2, 3, and 4, and the addressing modes 2 possible: direct and index, X is equal to 0 or X is equal to 1. Here 5 possible modes are there: X is equal to 0, B is equal to 0, P is equal to 0, N is equal to 1, N and I are 0 or 1. Okay, so there are many more possible. Also, like they are relative, B is equal to 1 and other is 0, and both can be 0 but not 1. Immediate, I is equal to 1 and N is equal to 0. Indirect means N is 1 and I is 0. Index means X is 1. Okay, so this was the first half of the module, and we'll be moving on with to the next part, which is the assemblers. Okay, moving on to the second half of the module, the second part is about assemblers. So what does assembler do is it converts the code which we write to the machine language code. Okay, in between it is in the assembly level language, it converts to machine level language. Okay, so that is the main thing of assemblers. So the source program will be written, and assemblers will convert into object code, and linker will convert into executable code, and loader loads into the memory. So under this topic we will be discussing each of these steps in detail. Okay, so assembler does 2 functions. It converts the mnemonic operation codes to the machine language equivalent, and converts the symbolic labels into their machine address. So the design of assembler can be as like it converts the mnemonic operation to the machine language, converts the symbolic operands to their machine address, and builds the machine instruction in the proper format, converts the data constants specified in the source program to their internal machine representation, writes the object program and the assembly listing. Okay, finally we need the object program. So the different data structures that are used for assemblers, like for example, if you want to perform the addition operation, you will be using the data structures int values, right? If you want to perform the addition operation on the 2 array of objects, at that time the data structure is the array, and if you have to perform the operations on the pointers and the dynamic memory, at that time the data structures will be linked list. So in the same way for the assemblers also there will be some data structures which will be used to store the values and perform the operation upon. Okay, so the first one is the op tab, which is the operation code table. Second is the symbol tab, which is a symbol table, and third one is the location counter. So in the operation code table, the first one what we have is the mnemonic operation codes, the machine language equivalent, and instruction format and length. Even if you don't understand what do these terms mean and it's confusing you, don't worry about that, just listen what I'm telling you. Okay, so by moving further and solving the practical examples, you'll get to know what actually it means. Okay, so during the there will be 2 passes in each stage of the assembler's conversion to the operation code. So there will be in the pass 1 we'll have the OP codes validation, and find the instruction length to increase the location counters variable. So we'll be encountering each line of code and then we'll be moving to the next one, and we'll be incrementing the location counter value. During the pass 2, it determines the instruction format 3 or 4 and translates the operation code to their machine language equivalent. Okay, so those are the two passes in the pass 1 and the pass 2. These two things happen. So in the implementation part, this is the operation code table. Here we have 3 rows, 3 columns: mnemonic name, operation code, and the format. Okay, means what is the mnemonic code? Means mnemonic names operation code for the given means for this what is an operation code and what is the format it is using. So everything will be specified here, and that will be referred. The second is the symbol table. In that we will have the label name, label address, flags, and the data type. And during pass 1, it stores the name assigned address from the location counter, and second part, the simple used as operand are looked up into the symbol table. Both of these operations will be seen practically by using an example. So it looks like this. It will have the label name here, value, flags, and the length, and this will be used to fetch the information and perform the operation. Location counter is just it stores the address assigned to each of these labels, and it starts from the start level, and it's processed during the pass 1, as in the pass 2 it will be referenced in the pass 2. Okay, so what happens, octave is used both in the pass 1 and pass 2. So when pass 1 is there, it converts the source program to intermediate file that will be converted in the pass 2 to the object program. In the pass 1, the location counter is generated, which is converted to SIMTab, and SIMTab is referred in the pass 2. Okay, because what variables were not defined here, that is stored here, and that will be referred in the pass 2 for the definition purpose. Okay, and similar directives are those like labels, which do not have the memory reference, but they are just used as a referring points. Okay, so those include start. It specifies the name of the starting address of the program and indicates the end of the source program. Byte, it generates the character hexadecimal constant occupying as many bytes as needed to represent the constant. Word, it is like the little assignment, like I is equal to 1. Instead of equal to, we are writing word I, word 1, then I will be assigned the value 1. And reserve bytes, so that many bytes will be reserved. Reserve word, that many words will be reserved. LTORG, create a little part that contains all the little operands since the previous LTORG. EQU, it is a symbolic name that is used for the equating purpose, and ORG is for the origin from where it is starting, and use is used for the program blocks. Base is for the base address. No base is for the indicates that the contents can be used immediately. It need not have a base address. Okay, so those are the assembler directives which you will be using in the program. Okay, so a simpler SIC assembler looks as follows. The usual format is first we will have the line number, then the location where it's present, and source statement and the object code. In the source statement, we'll have the label, operation code, operand, as well as the comments. Okay, so label will denote what is the label will denote the name, if the user is not able to remembering the label and all, so that will be specified as a starting location. And for the other purposes also, labels are used just as a reference point. Okay, and operation code will be there, the numeric value for that label, and operand will be there, means on what we are means performing the operation upon, and the comments is used for the explanation purpose. Okay, so in this example, first is the label, and this is the opcode, and this is the operand. Okay, and opcode is this one, like comp, and 0 is nothing but the operand. Operand is just the additional data where the means the operation is performed upon. Okay, so we'll be using the knowledge which we have now as till now to write the SIC XE programs. So this is the same programs which we have discussed in the SIC. So we'll be seeing what are the changes which are happening here. This rest all things are same. So first is the data movement operations. In the A register, we are storing 5. Then what we are doing, we are storing that in the alpha, so alpha will have 5. Okay, then we are loading into the register 90, and that will be storing in the C1. So that's all what we are doing. In the previous one also we had done the same thing, but 5 was defined as we have written here, right, 5 word 5. Instead of that, here in SIC XE we can directly use the immediate addressing. Okay, in arithmetic operations, beta is equal to alpha plus increment minus 1. Increment is loaded in S. Alpha, in the alpha, what we are loading in the A register, we are loading alpha, and we are means adding the registers. Source to destination means S is equal to S plus A. A is equal to A plus S. Okay, that we are doing, we are adding A plus S and storing in A itself. So these are the steps which we are doing, but in the previous one what we had done, we had stored in A itself and incremented in A itself, but here we are using 2 registers because S is a new register which is used for general purpose. Then we are subtracting 1 and storing the answer in the beta. Okay, and looping and indexed operations, here we have the gamma is equal to alpha plus beta, where alpha and beta are the arrays. So what we will do, first we will load into the S register 3 and load into T register 300. This is the starting address, this is the ending address, and we are starting from index 0. Okay, and each length is 3. Instead of just specifying 3 as a constant name, we are using the registers here. Okay, so that's the only difference between SIC and SIC XE. So you are starting from here. Alpha is stored means in the A register. What is stored is the alpha value at the alpha's x value. X value means 0th location. Alpha is an array, right? So 0th location of alpha is stored in A. Then add beta x means the beta's x location is added to the same register, and we are storing the answer in gamma, in x location of gamma means 0th location of gamma. Then we are adding the register value of s in x, and that means the incrementation, and we are comparing if it is equal to t. T means 300. If it's equal to 300 means all the words are added. If it's not, then it will loop. Okay, just slight syntax difference. Okay, and if you had understood the SIC programs very well, this will be very easy for you. Okay, so in loop and out loop, this for the input, this for the output. We are testing the device ready or not. If it's equal, if it's not equal, we'll keep on testing. If it's equal, we'll come here, read the data and store it into the data. Here also doing the same thing, we are fetching the data and outputting it. The subroutine to read 100 byte record from the input device into the memory. So jsub, read jsub is the subroutine jump, and read is the name of the subroutine. We are reading from here, we are starting from 0 and the target is 100. So we are testing each time, means the device is ready or not. If it's ready, we are reading the data rd in def, and we are storing the answer in the record of x value. X means the 0th location. Then we are storing in the first location, second location, and so on. Where we are incrementing the x value, we are incrementing here. Okay, if it is less than the final result means 100, we have to again loop it for the next one until it reaches 100. It will come here, and when it comes here, it will return to the subroutine. Okay, so these were the 5 which we are discussing in the SIC also. And these are the type of the questions which are asked in the exams. So you can expect this type of question to copy system software into another string. So firstly, you need to take the LDX. This is SIC program we had discussed earlier also, like how is SIC written and how is SIC XE written. This is the asked more number of times in the exam, SIC XE than SIC. Okay, we are loading into the X register 0, and we are loading a character str1 of x value. X value is 0, so 0th location of str1. So this is system software, right? I guess so. The s will be stored in the register A. LDCH means by default in register A only it will be stored. So s will be stored in A, and we are storing the character in str2's x position. This is str2 x position. This will be stored. Next will be fetched. Again it will be stored in next location, next and next location. Like that it will happen till we reach the end. So the string's length is 15. So until it reaches 15, it will loop, and when it reaches 15, it will come out of the loop. Okay, same thing we are doing in this also SIC XE program. Here we are, instead of using the words, we are using just the immediate address. So in X register we have 0, the target is 15. So in T register we have 15, and we are storing the first value of the str1 in the A register, and we are transferring that value into str2's first location. Then we are incrementing t and comparing if it's equal to the target value. We are incrementing x. X was 0, it will become 1. That will be compared with t. T is nothing but 15. So it is 15 or not. If it is less than 15, loop. If it's greater than 15, come out of the loop. Okay, so till it comes out of the loop, all the letters from the index value 0 to 14, so all those will be stored in the str2 one by one. Okay, so that's what the code which you have to write for the copying of the string system software to another string. Okay, and here are some more examples. If you want, you can skip this, but if you see this one also, you will be much more ready for the actual numericals which you are going to solve. Okay, so here what we have, write a sequence of instructions SI to set alpha equal to the product of beta and gamma. It's so simple. You have to just implement this instruction, alpha is equal to beta into gamma. So load into a register A beta, multiply gamma into the same register, and store the answer in the alpha. That's all. Alpha is equal to beta into gamma. And write a sequence of instructions for SIC XE to set the alpha equal to 4 into beta minus 9, and so A will be equal to alpha will be equal to 4 into beta minus 9. So load into register A beta and load into register S4, multiply both the registers MULR S and A, and the answer will be stored in A, subtract 9. So it will be nothing but 4 into beta minus 9, and that answer should be stored in alpha. So that will be in register A, that will be transferred to alpha. Okay, And moving on, we have the next one, write an instruction to swap the values of alpha and beta. So how do you actually swap the values? Suppose that there are two values, x is equal to 1 and y is equal to 2. So what we will do, we will take a temporary variable, store the x value in temporary variable, transfer y value in the x value, so it will be 2, here temp is 1, and we will transfer the value of temp in y, so it will be 1 and this will be 2. Like that we are doing the same thing. Alpha and alpha will be stored in a, and we are storing that value in gamma, and we are storing beta in a, and then we are storing the value of beta in alpha, and the gamma value which was stored, which was the previous alpha value, will be stored in beta. Okay, so gamma is used as a temporary variable. Okay, so that was for the swapping of the variables. And to perform the division operation, the same thing, load the in the a register beta, division, divide beta by gamma, and then again store the answer in alpha. Okay, so the next one, this is the question paper question, system software into another thing. This we already discussed. Just store the this is the starting address. It is a SIC program, so remember you can't use the immediate addressing, so you have to use 0 itself and define what is 0 at the end of this code. So here 0 is word as 0, and we'll be storing the first character of the string in the a variable, a register, and from that it will be transferred to str2. Like that we will do for all the words, and in each time we will be incrementing the x value. When x reaches 15, it will come out of this loop and it will means do the next operation. Okay, so this is the code for SIC's system software. You have to copy into another string. Okay, so this is the next topic, machine dependent assembler features of SIC. We have another one for SIC XE, which we'll be discussing after this one. Okay, coming to the machine dependent assembler features in SIC. So first we'll be looking on SIC, then we'll be looking for SIC XE also. Okay, so here what is there is, before moving on, you need to know these things. So you can open this document in a new tab and follow along. Okay, so here as you can see, there are mnemonics and format, opcode and effect. Okay, four columns are there. So what do this column means is, these are the opcodes. Okay, means opcodes, mnemonics, add are, this will be using a few of them, will be using more. Okay, so what are these formats, means in which formats it's used mostly, and what are the opcodes associated with that. Opcodes are the constant values for each of these mnemonics. Okay, because the computer processes numbers and hexadecimal values, not these letters. Okay, so we have to have opcodes for each of these things. And what are these effects, you need not worry about this one, because when you solve the example, you'll get to know what do these things mean. Okay, so these are the mnemonics, means you can refer this whenever it's needed. And yeah, that's all. Okay, so let's get started with the actual program. So in the exam, they'll not ask this much hard, and if you if you follow this one, and if you get to know this one, if you know how to solve this one, then you can solve any of the other program easily. Okay, so make sure this for the basic foundation, this is very hard as compared to the actual questions which are asked in exam, but make sure that you understand this one very thoroughly, then other programs will be very like a cakewalk for you. Okay, so let's get started and solve how to write the object code for the given SIC program. Okay, this is just for SIC. SIC XE also it will be there, it will be slightly different. Okay, firstly we'll be learning how to solve for SIC, then we'll be moving on to the SIC XE. Okay, so what you're supposed to do is, you'll be given with this code. Okay, like this code you will be given, and what you have to do is, you have to write the object code. Object code means these numbers you have to write. Okay, now it might seem for you like it's very hard to write what are these numbers, you even don't know what do these numbers mean, but actually if you know the pattern, you can easily write the numbers. I can give an example. I'll tell you to write what is the next number. Okay, if you observe carefully, you can easily write the next number, right? You can easily tell what is here. It's 56, right? So but if you just look suddenly, like without any thinking, then you will see how to write these numbers. It's very hard, right? But if you know the pattern, the thing is easy, right? So you have to get to know what is the logic, and how to means approach this question. Okay, so let's get started here. Firstly, this is the overall program. Okay, it has how many lines? 255 lines. Okay, so it has 255 lines, and these are the lines which is given to you, and the source statement is this whole thing. Okay, this is known as source statement, and source statement has four things here. These are the first column, second column, third column and fourth column. In the fourth column, this is just the explanation of what does this term mean. Okay, means this line means what, that is specified here. Okay, so this is just for the understanding purpose. It's like comments. Okay, comment. And these three things are there. These are the important things here. The first one is label, this is opcode, and this is operand. Okay, not actually opcode, but it's a slightly different thing. Let's see what it is. But you will be given it in this format. Okay, you'll be understanding what do these terms, each term mean, and what you have to do with each terms. Okay, after you have been given with these things, your first task is to make it like this. Okay, write label on top of this one, opcode on top of this one, operand on top of this one. Okay, these three things you have to write first. After writing these three things, one another thing which you have to write is instead of comments, you will be writing an object code part here. Okay, to write the object codes for each of the letters. Okay, after you have done that one, you have to include the location here, location as well as the length. These two things are very important. Firstly, you will be calculating location in the first pass. In the second pass, you will be calculating the object code. Okay, you will not get the object code in the first pass. Firstly, you will have to pass to the whole program and write the location means location values. After you get the location, then only you can proceed to write the object code. Okay, that's why this algorithm is two pass algorithm, right? Not one pass. Okay, so that's how we approach this question, and let's get started with the first one. I request you to open this PDF in a different device as well, because I myself will be looking at a different device and explaining the concepts. Okay, so firstly, how do we start is we'll be going through the basics of what are the object codes algorithm, and then we'll be actually solving the question. Okay, so going through the logic part, what is there here is, see, the following program contains a main routine that reads records from an input device and copies them to the output device. Okay, it reads from an input device and writes to the output device. So that is the main objective of this program. If you see from a bigger picture of what's happening here, see, this whole code is divided into three parts. This one part, this second part. Okay, this is known as int main, like how we write in C, right? C language, int main. And this is one function f1, this is one function f2. What does f1 do? F1 will read the record, means take the input, like C in. And what does f2 do? It will write the record. Write the record means C out. So we'll call this function from here. We'll take the input and store it in the memory, and we'll next we'll call this function to print what is stored in the memory. Okay, that's what the program is all about. Okay, so that's all what is written here as well. Okay, so here we'll be calling two times the function. First we'll be calling jsub. Jsub means the function call. Okay, wrec and jsub read record. When this is called, it will read the record and store it into the memory, and when that is over, we'll write the record and display it to the screen. Okay, and that's what the bigger picture is about in this program. And the main function calls the subroutine read record to read the record into the buffer, and the subroutine write record write the record into the buffer to the output device. Okay, these are the two functions which are used, read record and write record. Subroutine means function calls only. Okay, each subroutine transfers one record character at a time, because only IO instructions are available in read and write record, means one character at a time it is transferred. Since IO devices of two devices may be different, a buffer is used. So this is just for the better purpose, like you can go through it, like how it's actually happening. We are using a buffer as well, because speeds are different in the input and output device. And the program indicates EOF, which is end of file, and output device in the zero length of the record, end of the file is detected. The program terminates by executing R sub instruction, since it was called by the J sub instruction. What does this mean is, when you encounter EOF means what? End of file. Okay, when you encounter end of file, at that time what should happen is it should return to from where it was called, right? So suppose you have reached the end of the file, it will go to R sub. Okay, R sub means it will exit. Okay, so exactly C means we'll go through each line and see what do these terms mean and how it's happening, everything. Okay, so don't worry anything about the working part, just understand what's happening in the bigger picture. Okay, and procedure to generate the object code and object program. So these are the two things which you have to write: object code, then you have to write object program as well. Object code, just I showed you how it looks like. That's the same thing which you have to do in the final stage. So object code is these things. You have to write these numbers, Okay, these are known as object codes. Okay, you have to write this. After you have written this one, you have to write the object program as well. So how does object program look like? We'll be seeing now. Okay, so object program looks like this one. Okay, this is the object program. This also you have to write. Okay, so we'll be discussing how to write the object code, then we'll be learning how to write the object program as well. Okay, and so let's get started with the basics of the algorithm. So procedure to write the object code and the object program intermediate file. So we have assumed that the program starts at address 1000. That's the first thing which you have to look. Okay, now you can observe in the PDF, if you have opened in the different device, the first part which is written is line 5, and there you have location 1000, copy start 1000, right? That's the first line. If I show you here, the first line is this one, right? Line number 5, I'll be telling like this. Okay, line number 5, location 1000, label copy, and opcode start, operand 1000. What does this denote is that the starting opcode, its address is 1000, so from 1000 it should start. If this is not mentioned at that time, by default it will be assumed that the starting address is 0. Okay, so since it's mentioned that it's 1000, what we'll be writing is in the next part. See, initially this will be empty, right? So before that we will be writing 1000. By seeing what is present here, the same value will be writing, and next also we'll be writing the same value itself. Okay, like 1000 only. That's the first thing which you have to do. Then the next thing what you have to do is you have to write these values, right? The remaining values. How you'll write is, to write the next value you'll be adding 3, then again you'll be adding 3, again you'll be adding 3. Every time what you have to add 3. Now why we are adding 3? Why we are adding 3? Because see here, return address, these things. Okay, these things are having the byte 3. Okay, whenever you encounter these type of things, you will be writing 3. Okay, adding 3 3 3 3. Only the difference will happen at this case. Okay, here why 1000 is getting added, because we have 4096. 4096 means in hexadecimal it will be 1000, so there only you will be adding 1000. Okay, means 1039, you reach till here by adding 3, and after that you will be adding 1000, so it will be 2039, and still you will be adding 3 itself until you reach like an input byte and all. Okay, when you reach input byte, at that time how much value is this one, that much byte you will be adding. Okay, input byte, what value is this one, that much value you will be adding. This is nothing but 1 byte. Why is it 1 byte, f1? Because f1 can be represented in hexadecimal as f is 1111, I guess, and 1 is 0001. So these are 4 bits, and 4 bits which are 8 bits. 8 bit is nothing but 1 byte, right? So that's why you'll be adding 1 byte for f1. Okay, make sure that it's in hexadecimal, so you'll be adding the same values. Okay, so you'll be adding just 1 here. After this one you'll be adding 1, so it will become 205D to 205E. Okay, and that's the same thing here. And after that 3 you will be adding, and for output also the same thing, input and output byte. For byte you'll be doing the same thing. Here also it's 1 byte only, so you'll be adding 1 byte at the last. Okay, after 2079 207A, and you'll not be writing the object codes. Okay, that was about the lock CTR. Just let's focus on the lock counter itself. So these are the instructions what you have to follow to write the location values. Okay, pretty simple, right? You'll just have to add 3 except the few cases which I have discussed now. Okay, and one more thing is that if word is coming here, okay, these things are okay, it's all the same, in the same category. If word is coming, at that time also you have to see each word is how many bytes. You remember, right? If we write 3 bytes here, that will become 1 word. So for word also you'll be adding 3 bytes. Okay, same thing. Even if it is 0 here, you'll be adding 3 bytes itself. Okay, and for EOF also you have to do one different thing, because byte is present here in the input and output. Also byte was there, if you remember. See, for byte it is there, right? Input, and for output also byte is there. You had added 1 byte, right? But in the EOF, what you will do, EOF is not in hexadecimal. Okay, what do I mean is, this is not in hexadecimal. So if it is not in hexadecimal, you have to convert each letter into hexadecimal. What is hexadecimal equivalent of E? It is 45, right? if you see the hexadecimal value of E, it will be 45. For E character I'm talking about, by using ASCII values. So ASCII value of A is equal to 65, like that. For E it will be like, I guess, 70. When you convert 70 into hexadecimal value, you will get 45. Like that. For O also you will get one thing, for F also you will get one thing, okay, by using the ASCII values. So those things are nothing but 45, 4F and 46. So these three values you got, and these are how many bytes? These two are 1 byte, 1 byte, 1 byte. So total is equal to 3 bytes, right? So here also you'll be adding 3 bytes, like that. You have to see and add, okay. Rest of the things are same. So that was the first step. We have to find out the location addresses. So if I show you in the theory, what is written is that first and foremost write the location counter values, okay. Start with 1000 and add 3 bytes for each instruction. As we had done, we had started from 1000, then added 1003, and then moved on further, okay. So that's what which we have done. And also one more thing is that okay, we'll be seeing that at the later stage, but for now it's starting from 1000 and adding 3 bytes, okay. Now there are few exceptions. That exceptions are written here. For byte C, EOF count the length of the constant and add that many bytes. Means EOF we calculated, right? It is 45, 40, 4F and 46, I guess. So those three things were added by means 3 bytes in total. And if it is RESW and it's written 2000, that means reserve word 2000 words should be reserved. If 2000 words should be reserved, how many bytes will be reserved? Into 3, right? 6000 bytes will be reserved. 6000 bytes means if you convert 6000 into hexadecimal value, what answer you get, that answer should be added, okay. Means we are just adding 3 at each stage, right? 1000, then 1003, like that we are doing. But when you get RESW 2000, calculate the number of equivalent bytes, convert that byte into hexadecimal value, add that hexadecimal value, okay. So if we see an example, it's actually like where we had added 1000 is here, okay. It is actually RESB. So 4096 was directly converted into hexadecimal value and added because it's already in bytes. But if it was RESW, if it was 1000, we will have multiplied 1000 by 3, it will be 3000. Convert 3000 into hexadecimal value and that add that many. Instead of 1000, we'll be adding 3000, okay. So that's what the difference is between RESB and RESW. So here see, it's RESW only, but it is 1. So 1 into 3 will be taking place. 1 into 3 is 3. 3 will be converted to hexadecimal, that is 3 itself, and 3 was added. So it is 10362 1039, okay. Okay, that was the basic part of RESW and RESB. Okay, if it is 1 means 1 into 3 is 3, you will be adding just 3 bytes. If it is RESB, 2000 only will be added after converting to hexadecimal because already it's in bytes. And if it's 4096, that will be converted to 1000 and that was added, the same thing. If it is word means 3 bytes, so 3 bytes will be added, okay. That is the first thing which you have to write. It is the location counter values, okay. These are the values which you have to write, okay. Now even if you don't understand totally, it's fine because we'll be solving examples by considering each line. So at that time hopefully you'll understand, okay. So don't worry, just listen what I'm telling, okay. After you have done the location values, the next step is to write the object code, okay. That's the main thing. Now how you will be writing object code is, first let's go through the theory part. So it's better if I just explain you practically, right? Because reading the theory won't give us much practical overview of what's happening. So let's go means understand it practically itself, okay. So by taking an example, now see, you have 5 here, line number 5, location value is 1000, and here it's copy, start, and 1000, okay. So one thing you need to remember, for all the assembler directives, assembler directive list I had shown right previously, like it was start, end, and all. If I show you again in page number 36, you can find that there are the assembler directives like start, end, byte, word, RESB and all. So these words do not require the object codes, okay. They do not require the object codes, that you have to remember, okay. So if they do not require the object codes, in that place it will be empty. Means what is the first line? The first line is start, opcode is start, it's an assembler directive, it will not have any object code, okay. If I show you another example, RESW, RESB, those things also are object codes. They do not have the those are the assembler directives. They do not have the object codes. Okay, and one more is this one, the last one, end also doesn't have any object code. Okay, it's empty here. So that was the first observation which I had to do. And moving on, if it does not have an object code, we are ready to move to the next line. In the next line, what we have is 1000 and the length is 3. First STL return address 14. How to write 141033? Okay, this is the task which you have to see. Now to write 141033, how I got this number is, observe two things. Label is just an assigned value. Okay, it doesn't have any in memory address and all. The only thing which you have to focus is opcode and operand. By using these two, you will be writing object code. Okay, what two you will be using? Opcode and operand you will be using to write the object code. Remember these two, this thing very means precisely. So what is the opcode for STL? STL opcode, it is fixed like I had shown you here, right? You have to look at this one and you have to write it in that way. So if you look at here, what is STL's opcode? See here, STL's opcode is what? 14, right? So that value you have to take. So for the simplification purpose, you will be given with those values in the exam as well. Means in the question itself, it will be given the opcodes for the mostly used mnemonics. So you need not worry about the opcodes. Like for example, for this problem, we have the opcodes here given to us. Okay, like this, in the exam, whatever the mnemonics are used for those, the corresponding opcodes will be given to you. So you have to see which opcode is currently you are encountering. It is STL, right? For STL, what is the opcode? 14. So that 14 value you have to take and write first. Okay, so you'll be writing 14 first here. 14. Okay, after that, what is the next value? How I got 1033 is, you have to see this one, RET ADR. RET ADR, where you can find is here. You have to find out in labels. Okay, in labels you have to find RET ADR. Okay, where do we find RET ADR is here. Underline it and underline the value of it, means the address of it. It is 1033. So that's what I have written here, 1033. Understood, right? So to write the object code, first check if it is a similar directive. Don't write the object code. If it's not a similar directive like STL, write the object code. How do you write the object code? STL, start from here. You have to just consider opcode and what? Operand. So STL's opcode is 14. They have given, they'll be given, you'll be given with it in the exam paper, the value, and you have to see the next RET ADR. What is the address? You have to see here. Come to this part in the labels column. There, what answer you get? 1033. That you have to write here as 1033. Okay, that's the first step. Means that's all what you have to do and write the object codes. If you see another example, all are same. Okay, like you have to come here, start from here, object code. The JSUB value of opcode is given as 48. If you see the means below where I had shown you earlier also, if you open the PDF, there you can see the JSUB value is 48. So I have written 48, and the next one is RDREC. Okay, now in the labels column you have to find out where is RDREC. RDREC is 2039. So what I have written is 2039 only. After 48, 2039, 48 from JSUB. Same goes for LDL length also, comp 0, JEQ and fill, JSUB WREC and JSE loop. In all these cases you have to do the same thing itself. Okay, and the difference comes here in RSUB's opcode is 4C, because since it's not written anything here, you will be writing zeros. That's one difference. And another difference is here, if it is word, you'll be just writing zeros, and what is the word value, that will be writing like 3. Okay, word first zeros, then the word means the value is 0 here, so you'll be just writing zeros. And for the assembler directives like RESW and RESB, you'll be not writing anything. Okay, and where is the another difference? Another difference is here, if you get like C of EOF, at that time you will not do anything for the byte, you will be just writing what is the equivalent of EOF here, like how you did for word, right? 3, you just wrote 3. For 0, you wrote 0. For byte also you have to do the same thing. EOF is there, convert it into hexadecimal and write the equivalent value. Okay, and let's see the explanation part for each line itself in the theory part here. So see, these are the differences. if you start from here, okay, let's start from here. These are the things which were given to us. So we had done this one, we are just incrementing 3 bytes and all, and we had written these values, log ctr values, that's done. And here the object code for each line. Okay, so this is the first line 5. So what you'll be doing is the same thing, stl. For stl we'll be writing 14, that's the opcode. For return address, where you can find in the labels column return address, what address is here, that we'll be writing in the this part. Okay, and if it is no operand, as I told you in the R sub, there was no operand, you'll be just writing 0 0 there. Okay, if I show you here, what I'm trying to say is this one. Okay, here you had nothing there, so just R sub value is 4c, and instead of this one, you'll be writing zeros here. Okay, that's what the exception is mentioned here. So yeah, that's one thing. And another thing is stch, that opcode is sh and indicates indexed addressing. Okay, here slightly different thing is happening, so observe carefully what's happening. stch, okay, that's our object code is sh. If I show you here, and not sh, I guess it is 5h. So let's see what is the stch. It is 54. Okay, so I'm taking 54 value, and we'll be writing this table. You remember this table, right? For SIC, the table is, first you'll have opcode, then you'll have index value, then you'll have 15 address. Okay, this I'm just talking about SIC. If you consider SIC XC, there will be like n and I bytes and all. We'll be discussing that in the later part. Okay, for now it's SIC, so it will be this part. And what is the opcode? Opcode is nothing but 54, so you have to write 54 here. 101 is 5, 100 is 4, that you have written. Okay, 54. Then the index value, since comma x is there, it's a slightly different pattern of the address value. So x is present here, so x value will be 1, you have written 1 here. And the address, how we will get the address? Buffer. Okay, buffer is written here. So what you have to do, in the labels column you have to find buffer. Okay, in the labels column you have to find buffer, means here you have to find buffer, and what is the address associated with that, where you can find buffer. Buffer can be found here, and what is the address associated with that? 1039. So that value will be taking and writing in the address part, 1039. Okay, if you write 1039 here, 1039. After I have written this one, you have to consider 4 bits at a time, like these 4 bits, it's 5, these 4 bits 4, then next 4 bits it is 9, and these 4 bits 0 3 9. Okay, so what answer you get? This is your opcode. So basically you did nothing, you just took the line here. In the line you saw that it is comma x, so I had to do something different. Take this opcode from the given values in the opcode in the question, write the opcode equivalent here, and x is present, write n x value 1. After that, address of buffer, find it in the labels column, what address is present, that address you have to write here. Take 4 bits at a time, make groups, and write the answer here. That's your final answer for object code 549039. Right, 549039. That's what it's written besides the line number 160, I guess. Yeah, 549039. Okay, that was another difference. Let's see what are more exceptions, if so, present in the program. For same for line 225 also, here also is the same thing. LDCH, it is 50, so you'll be writing 50 here. X is there, so you'll be writing 1 here. After that, the address of buffer you'll be writing, and you'll be writing the final answer in the object code. Okay, so yeah, that's all the differences what you will encounter in the object code. Rest all is in the same way what I have told you. Just look for still what the code is, for return address. In the labels column, what address you find, that you have to write in the last 4 means bit positions. Okay, so in that way you'll generate the object code, and object code is not defined for the assembler directive like start and end. Okay, and resw and resb. So these are the few key points which you have to keep in mind before solving this type of question. And in that way you'll get the codes. Okay, object codes. And after you have got the object codes, the next step is to generate the object program. Okay, so object program, first let's discuss the theoretical part of how the object program looks like and what you have to do in it. Okay, so if I show you, and I already showed you how the object program looks like. It looks like it looks like this, like these things you have to write. Okay, if you observe carefully, there are 3 sections here. First is the head section. another is T section, this is head section, in the top one line, and in the ender section which is one line, and this is the text section which has multiple lines. So how to write each of these lines, what are these things, we'll be discussing now. Okay, so it's better if you open this object program in a different tab, so it will be easy for you to refer what I'm trying to say. So let's see the format for object program. Okay, see, these are the same things which I had discussed. Okay, how to write the logctr values, that's the first step. And after you have written the logctr values, just how I explained you, do the same things, you can easily get. If you want, you can go through this one, and that's the same thing, nothing new I have mentioned here, the same things what I have already told, like by using a practical example. After that is done, means the object codes are ready, you have to write the object program. Okay, how to write the object program, three things are there. Okay, header record, text record, and end record. Okay, so in header record you can find four things. Column 1 is you have to just write h, column 2 to 7 program name, column 8 to 13 starting address of object program, column 14 to 19 length of object program. Four things we have to write. Okay, for example, if you have to write the header for the first means the whole program, you have to write one header only, right? Okay, so this is the line 1, which is line number 5, and this is the label name. Okay, which is same as the name of the program. The first label name is the same as the name of the program. Okay, and the starting address will be specified here after start. So three things you got here, this is the name of the program, and this is the starting address, and the length of the program I will calculate. The first line is line number 5, the last line is 255. So the answer which you get here, this is the last code. So the last code minus the first code, in that way you will get the total length. So I've got three things, copy is the name of the program, this is the starting address, and this is the length. So these three things only were needed, right? Three things, program name, starting address, and the length. So by using these three things, you will be writing the object code. First you will be writing h, after that you will be writing this caret symbol here, then the name of the program, copy, then again caret symbol, starting address you will write 0 0 1 0 0 0. Okay, like in 6 bits you have to write. Okay, after that again caret symbol, and after that you will write the length of the program, which is 107a, and before that 2 zeros. So this is how you write the header. Okay, that's the first line in the object program. Okay, if you observe here carefully, the object program is the first line here, h, copy, and starting address, and the length of the program. Now let's see how to write the end program line, and after that we'll be seeing the text as well. So here only two things are there. If I just tell you orally what's happening, e you have to write. Okay, e, then caret, just like how you wrote h caret, and after that this the starting address. Okay, that's all what you have to write, 0 0 0. Okay, this is just the end lines format. Now let's observe what is happening here in T part. Okay, so in T part, if you observe carefully, what's actually happening is how many columns you have. The first column will be written as T, and after that you will be writing in the column 2 starting address for the object code in the record. Okay, means the whole program except the means the whole program, whole program will be divided into different parts here. So the starting address of this part, that will be written, starting address of this part, that will be written. So for each part there will be written different starting addresses, and the next column 8 to 9, it will denote the length of the object code in this record. If this is the whole program, you have divided like this, what is this length, that you will be writing in the column 8 to 9. This length also will be written, then this length, and this length. Okay, and the last one, object code represented in hexadecimal, 2 columns per byte of object code. Let's see what does this mean. Okay, so this is the total program. This is the line number 10. It's starting from actually line number 10, because first line is just the assembler directive. So here we have 1000. Okay, and the first is written, this is the first line of code, and STL, return address, and this is the object code for it. Okay, right, what I mean is this one. Okay, this is a line number 10, and here it is first STL, return address 141033. The same line is written, right? And as I had told you, the whole program will be divided into different parts. Okay, if this is the whole program, it will be divided into different parts. So the first part is from line number 10 till line number 55. Okay, this is the first part. For this one, T will be written like that. From 55 to another T will be written, another T will be written, like that. Many T's will be written. That's what the final object program is looking like, right? This for line number 10 to 55, this 55 to I guess 100, then 100 to 150, 150 to 200, 200 to 250 I guess. Okay, so in that way for each block one test record is written. Okay, so if you see the object code, it is divided into different parts. This is the first part, line number 5 to line number 55, then 50 to 90, then the third part is from here till here, and then the fourth part is from here till here, and the fifth part is from here till here. After you have written that one, you have to after you have divided the thing into blocks, then what you're supposed to do is, okay, you have to write t and you have to divide this into blocks and calculate how many bytes are there. How do you calculate bytes? This is starting 3 bytes are there. Okay, 3 bytes, and ending also it is 3 bytes. So how many total how many words are there? 10 words are there, right? So if 10 words are there, the total number of bytes will be 10 into 3, that will be 30 bytes, and if you convert that into hexadecimal value, it will be 1e. Okay, length of object code. So you got the total length 1e, that will be writing here. This is the starting address of the block, which is 1000. This is the starting address 1000, you will be writing t test record, 1e is the length. Okay, after that this is the object codes we will be writing, 1033, then the second, third, fourth, and the last one here. Okay, by separating by carets. That is the how you write the test record. This is the first line. For the second line, what you will do, you will do the same thing. You will start from the next one. Okay, if I show you the object code here, for the next one also you will be doing the same thing. You will start from here. The starting address is 101e, and the length you will calculate how much length is there, means the starting location minus ending location, you will get the total length, and after that you will be writing the total length, starting address, and what are the object codes you will be writing separated by carets. Okay, that's how you will write the second record, third record, fourth record, and so on. Okay, all the records you have to write, and finally the code will look like this. After you have written for all the blocks, the test records, the code will look like this, and this is your object program. Okay, this is what you have to write in the exam as well. Okay, see this example, if you understand, it's a very basic means for your foundation it's very good. Okay, it's a bit means very hard as compared to what is actually asked in the exam, but if you understand this one, it's very easy for you to write the actual answers. Okay, like what question they ask. Okay, so in the exam it will be a pretty simple one, it will not be this one big one. So yeah, let's move on what's further here. So this is a symbol table, this like optional for you to make, just for the reference. First, what is the address, C loop, what is the address, and fill address, like how we used to look at the address right here. What operand we get here, like return address, we used to come to this part, find in the label where is return address, what is its address associated. So instead of that, it's directly written return address is present at what location. That is known as symbol table. Okay, in that's just for your reference, like directly it's written return address is at 1033. Okay, like that. And after see, this is all what you're supposed to do in an exam. And now like for your deeper understanding, after this is done, the object means the loader loads it into the main memory. Okay, if you understand this one as well, the last part of this module will be very easy for you. Okay, like how does loader load it into the main memory? After you have got the object code, like what are the object codes present here? These are the object codes, right, which we had got 14103348048203 48239, like what we have got here. Those are the object codes. So those object codes are written in the memory as follows. You'll be starting from 1000 here, you'll be writing from 0 to F, and after that two letters you'll be writing here, 1 4 10 33 48, like that you'll be writing till here. So here it is what, 102D. Till 102D was the first text area, right? See, text area was till 102D. This one you will be writing in the memory and you will be marking it as the first area. Okay, that's how the loader works. It will load it into the memory in this way. Then the second part also will be loaded. Return address and length, what do these terms mean? Return address and length did not have any number associated opcode with it, because you see the object code here, return address and return length, where it is, it's here. So here it did not have any values here, just return address and length. It had 33 bytes, so we'll be just writing return address and length there itself. Okay, and buffer was 1000 bytes, so we'll have to allocate 1000 bytes. So I've done here like we have left 1000 bytes here for the buffer part, and after that it starts from here. Okay, and each of these block represents address. Okay, like what is the starting address for the first opcode? 1000 and 0 means 100 only. Then what is the starting address of the next code? It is 1003. From the next opcode is starting from here, right? 482039. See, if you observe in the diagram, means the object code here, the second address is starting at which location? 1003. So that's what it's representing in the main memory as well. Okay, so that's all what you have to do in the like how to convert the SIC program. So this was for SIC program, SIC to object code, from object code to object program. Okay, so this is what you have to do in the exam as well. But in the exam mostly they will ask about SIC XE, so we'll be discussing that as well. What are the changes you need to make to solve the questions under the topic SIC XE. Okay, we'll be discussing the same example and we'll be seeing what changes are happening in SIC XE. And let's move on to the next one, which is the algorithms, pass 1 and pass 2. Okay, if you have understood the means the logic of how to solve these questions, the algorithms are pretty simple because that's the same thing, right? Two passes. In first pass you'll write log CTR values, in second pass you'll write the object codes. Okay, that's what the same thing is happening. So let's discuss the algorithms. Moving on to the algorithms of pass 1 and pass 2 of the assemblers, we have the following. Like in pass 1 will be what we did, the same things are mentioned here. In the first pass we will be going through the means the statements which are given to us, and then we will be assigning the log CTR values, right? So that's what it's happening here in the first pass. And in the second pass I will be looking those LCTR values and writing the object codes. Okay, and from the object codes you are writing object program and doing the assembly linking. So let's see the actual algorithms of what they are. So this is the first algorithm. Okay, this is the first algorithm, and you'll be easily able to understand if you had understood the actual numerical how it's solved. So what's happening first is we'll be beginning and reading the first input line. If the first input line's opcode is start, then we have to do the following, right? If the opcode is start, then only we'll be doing the following. If it is not start, at that time the log CTR value will be 0. If the value is start here, then what the operand will be there, like in our case it was 1000, so the starting value was 1000, right? So log CTR became 1000. So if it is start, at that time save the operand value, which is nothing but 1000 as the starting address, initialize log CTR to the starting address, write the line to the intermediate file, read the next input line. Means we are just initializing to the intermediate file and then we are moving to the next part. And what we have here is like in the else part, if it will be 0, so the if else part is over. Then both will come to the while part. While opcode is not equal to end, means till the end we will run this program and we will do the following. So here what's happening, begin, if this is not a comment line, then means if it's not a comment line, then only we'll be considering that. Okay, begin, if there is a symbol label field, so in the label field you have to search for that label, what does that label mean, and whenever we don't get that label, we'll be saving that label as well as the log CTR value into the sim tab. So for the future purpose we will be saving that. So yeah, we are just searching the label. If it's present at that time, we are seeing what that label is. If it's a normal label, then we'll be adding 3 to log CTR. If it's the word, we'll be adding 3 to CTR. If it's the RESW, reserve word, at that time we'll be multiplying 3 with how much reserved bytes are there, right? If it is like RESW 3, at that time 3 into 3, 9 bytes will be stored, right? So that's what we are doing. And if it is a reserved byte, then just add how many bytes are there in that operand to the log CTR. And if it is byte, at that time you have to find the length of that byte, how many bytes are being specified there. So we'll be finding that length and adding the length to log CTR. Okay, so in that way we'll be doing the things, and this is just the else part and all. So we are writing the intermediate file while not end that's happening, and we are saving the log CTR and starting address to the program length. Okay, in the pass one we are just initializing the log CTR values. After you have done that, in the next pass what we do, you'll be seeing from the log CTR values and sending the object codes, right? So we'll be starting from here. If it is start, write listing the read next input line. Okay, and if start, write the header record to the object program, initialize the first text as text record. Okay, so we are starting from here and writing the header record. After we have written the header record, then we'll be means running when till the opcode is not equal to end, we'll be running. And if it's not a comment line, and then we'll be searching for op tab in the opcode. What is op tab? Op tab is nothing but what is the operand, that for that what is the opcode that we'll be searching. If it is found, we'll be using that. If it's not found, we'll be setting that value from the sim tab. We'll be searching and saving an operand. Okay, so after we have done that, if the opcode is found, then we'll be setting the opcode as byte or word. Means if it is byte or word, then object will be fitting in the current text record, and write the text record to the object program, initialize new text record. So text record is nothing but that thing which is starting from T, those things, right? So we are doing two things here. Firstly we are writing the means opcode, like for STL it was 14, right? And what is the log CTR value for the given address, that one we are writing here. Both things we are searching here and writing here. Okay, and then we'll be reading the next input line till the end program. Okay, so this is how the pass1 and pass2 algorithm works, and that's all about the algorithms that in the exam it's also asked like repeatedly, so you have to know how it works. Okay, and moving on, we have the SIC XE. Now we'll be dealing with SIC XE, how to write the object code and the object program for it, just as how we did for SIC. Okay, so few things which are changing here is the total number of registers are 9, before it was 5. So the new registers are BSTF, and these are the numbers associated with that. Okay, and data formats: integer means 3 bytes, character means 1 byte, float means 6 bytes, and there are 4 formats. The first format is 1 byte, like if it's just a single instruction. So for that just the opcode is sufficient. If it's a comparison or adding operation, at that time the operands are also required, so it is total of 2 bytes, 8 bits, and here also 8 bits. And if it is like the format 3, in that we'll have NIX BPE also, so those are present here, along with 12 for displacement. That is format 3. For format 4, only one difference, 24 address instead of 12 here. Okay, and it will be represented by plus. Okay, we have 20 address lines, so we can have 2 power 20 addresses. Okay, and addressing modes can be determined based on the 6 bits. So NIX BPE, if it is 1 and 0 means indirect, and immediate is 0, at that time it is indirect addressing. If I is 1, it is immediate. If both are 1, it's not immediate, not indirect. If it is 0 0, it is simple addressing. And about X, if it is 1, it's index. If it's 0, it is direct. The same way we have for B and P also. B means base, P means PC relative, and E means if it is 0, it is third format, and if it is 1 means it's fourth format. Okay, and different addressing modes: indirect addressing using @ immediate addressing hash, extended format plus, this is the format 4, index addressing operand comma X, character string C and single quotes, base register base, and current value of PC by star. Okay, so we'll be using these things, as well as these are the ranges given to us. You can go through it, and the negative numbers are represented 2's complement, that you already know. So what is the procedure? The procedure is same. We will be doing the same thing. So we'll be first assigning the log CTR values, and after that we'll be assigning the object codes. Okay, so here are some basic information given, like if it is in format 3, here we'll be seeing the format as well. Okay, if it is format 3, add 3 bytes. If it's format 2, add 2 bytes. If it's format 4, add 4 bytes. Okay, if it is a reserve word 2000, at that time 2000 into 3, because it's word, one word is 3 bytes, so 2000 words will be 2000 into 3 bytes. This is the address which is to be added. Okay, if it is RSW1, it's just 3 bytes which are getting added. If it is bytes, means 2000, it's just 2000 itself. Convert it into hexadecimal and add those values. Okay, if it is 4096, means it's in the hexadecimal 1000, so that many bytes are added, means 1000. In hexadecimal, that many bytes are added to log CTR. Okay, and if it is EOF, calculate what is the value of EOF, and that one will be added. Okay, and once you are done with the log CTR calculation, then finding the program length, end address minus start address, that will be stored as program length. And after we have stored the program length, then we can start calculating the object code, again passing through it and seeing the operands, seeing the log CTR values, and again storing the object codes. After the object codes are stored, just convert it into object program as you have done for the SIC. Okay, that's the same thing here, what I have just told. So let's see what is the source program. The source program is same just as the previous one, but here's a slightly different concept. Is like here hash is there and here plus is there for format 3 and 4. So those are the different things, and here directly 0 is written, but in the previous case it was written like ZERO, and zero's definition was here 0 word 0, right? But instead of that you can directly assign by using hash value. Okay, so that is the int main, and this is the read record buffer, and this is the write record buffer. So the same things what is happening, let's consider each code one by one. Here the object code will be different because it's NIX VP is also there, so in that way object code will slightly differ. But let's see what is the object code. Okay, first you will be writing the logctr values. It's not specified here, so it is 0. We'll be starting from 0. We'll be writing here 0, then next is 3, and next after that we have here just that it's the base means opcode here, and it is a similar directive, so we will not be assigning anything here, and there will be no location as well as the object code. Okay, so we'll be starting from the first one. We'll be considering each line one by one. So I request you to open this PDF in a different device so that you can see what's happening here, as well as I'll be explaining each line one by one. Okay, so the lines are written, I'll be explaining one by one each line. Okay, so let's go to the explanation part. You can open this PDF in a different device so that you can refer it, okay, simultaneously. So we'll be starting from the line number 10, because the top two lines don't represent any means opcode which is not a similar directive. As you can see, the first what you have to do is you have to just look at the address here, it's 0, and the label given here. Okay, it's first. Then after that, if you have to write the object code, then you have to see what is the opcode for STL, which is 14, and return address, what is the logctr value that you have to look. Okay, means 0030. After that is then it is the format 3, because operand is not the operand is memory address. Okay, means return address is a memory address, and that's the format 3. Whenever it's a memory address, it's the format 3. Okay, and yeah, that's all what is present here. So we'll be starting with this one, 14. What is the opcode for 14? Actually it's not 14, it's 14, so it will be 0001, and it will be what is for 14? 1110, right? So this is the opcode. So for 1 you will be writing the same thing here, but for 14 you will be just taking the sorry, it's 14, right? So it will be 0001, and it will be 000, right? Sorry, not 1000, but 0100. Okay, so 0100 is for 4, and this for 1. So 1 you will be writing it same, so you have written 1 here, and for this one you will be removing the last 2 bits. So if you remove the last 2 bits, you will be remaining with 01. That's what you will be writing here, and it's means immediate, it's indirect and immediate, so you'll be writing that as 11, and after that what we have is 0030. So 0030, first you have to calculate the displacement. Displacement nothing but target address minus PC value. Target address is what? Target address is the return address, which is 0030, and logctr value is 0003. Okay, so when you subtract, logctr value is the next value. Okay, means location of the next instruction to be calculated. This for this current instruction, what is the next instruction in line number 12? So that what address is there, that is 0003, right? So that value will be taking. Okay, and we get here 002D, but we should just take 02D because it's of 12 bits, so each will be represented by 444 bits, so it will be total 12 bits. So 02D I have written here, and it's format 3, so E will be 0 in PC relative, so P will be 1, B is 0 here, X is 0 because it's not indexed, not base relative, but both of these will be 1 because it is both indirect and immediate. Okay, so that's how you will be writing the opcode for this one. So what answer you get here, take the 4 bits one at once. So if you take this one at once, and this one at once, and this 4 bit at once, you'll get the answer. Okay, sorry, it's not immediate and not indirect, so n is equal to 1 and I is equal to 1. Okay, so the object code will be this one. Just take this has this represents 4 bits because you remember 0001 we had taken, so that represents 4 bits. That will be taken as such. This also represents 444 bits, so that also will be taken as such, and this will be taken in pairs, 4 and 4, so it will be 72. So the object code for this line is 17202D. Same goes for this one also. Here in object means first we have to find out which format it is. It is in direct addressing because it's immediate addressing, so we need not worry about anything. Just calculate the displacement like this, TA minus PC. What is the PC value? PC is 06 because the next value of this one is 06, and this value is nothing but what is this length value. That also you can easily get to know from the information given to us. Length is defined as 0033, that is the address value of length, so that value will be taken here. When you subtract, we'll get 002D. So 02D will be written here, and this is PC relative, format 3, and B and X is 0, N is 0, I is 1, immediate addressing because hash is there, and this is 6 and 1. Why I have written 6 and 1 0, actually 1 0, okay, 6 1 0 I have written. So it is 68, right? 68, how you will represent? For 6 you will represent 0 1 1 0, and after that for 8 you will represent 1 0 0 0, right? So for this will be taken as 6, that will be written as such, and this one last 2 bits will be cut, so this will be 1 0, so 6 1 0 I have written here, okay, 6 1 0. Then this will be taken as such, this will be taken as such. For 4 you make the pair and find out what is the value, that answer you will be writing here. In the same way we have to do for all of these. There's the differences I will tell. Plus is here, so it will be format 4, and what is the value 48 and what is this value 0030. Then calculate the displacement. Displacement is the same as the operand value, which is 01036. 1036 is the value of this one. So it's the value of RD-Rec. So PC value for RD-Rec is 1036. That's why I've taken there 1036. Okay. So yeah, we are here. This was RD-Rec value, and that one we have taken here because it's extended to format 4. At that time we have to take the same value. Okay. After that it's not immediate, not indirect, so n and IR1, so set n and IR1, and 48 you write 4 as such, and 8 as 10 only because the last 2 zeros will be removed, and these values, like it's not PC relative, not base relative. E is 1 because it's format 4, and this address is written here using 5 bits. Again, so the answer will be 4B101036. Here also it's the same thing. Length, the displacement will be TA minus PC. So TA length is target address, which is 0033, and PC value is this one, which is the next value of this one. So that answer will get 026 right here, and it's in not immediate, not indirect, so both are 1 here, and this is 0, it's in not indexed, not base relative but PC relative, so P is 1, and here it is 00 because the opcode for LDA is 00. Okay, so 0 here, and from 4 zeros 2 zeros will be written here. So like that only for all of these. Let's see if any other exception is there, what we have to do. So here also it's the same thing, just the displacement operand is here 0, so we are just writing here zeros, and here also it's the same thing, it's within the range, so we are not doing anything. Let me just tell you where the differences actually happen. So yeah, here one difference will happen. EOF, the value is 002D, and this is the next value of this one is 001D, so it will be 001D, 01D, and these two are taken as 0 because it is LDS opcode is 0. So this is also same thing, no, it's not any different. So here what we are doing, it's immediate address, so 3 value is taken, 003, and its immediate value, so I is 1, rest all are 0, and in the LDS value is 00, so we have written here 00. Okay, so what format 3, and yeah, see here the difference is coming. EOF, the hexadecimal value is 45, 4F and 46, so that's all what we are writing. We're not doing anything else. The answer will be this one only. Okay, 45, 4F, 46. Coming to these type of codes, here we have one command here, and just one register is here. If register is present, remember the values of registers, A is 0, X is 1, and so on. So what we'll be doing is, the clears opcode is B4, so we'll be writing B4. Then for X it is 1, right? So we'll be writing here 1, then adding a 0 at the last. Okay, so that's what we are doing here. This register to register mode. As I told you earlier, if register to register mode comes, then what you have to do, that we'll be discussing. This is the thing which you have means what I told you. Okay, see here it is clear and A, right? Clear is B4. Before I've written A is 0, so I've written here 1 0, and at last add one another 0. Same thing goes for S. Clear is B4, so B4 is written. For S, what is the value? S, it is 4, so 4 I have written and added one more 0. Okay, like that only we have to do. For the comparison operator, which two you are comparing? 0 and 4, A and S, right? So you have written 0 4, and A 0 is for comparison. Here also the same thing, here also the same thing. Okay, and yeah, here also all the things are same only. Here 4096 is taken as 1000, so 1000 is written here. Rest all things are same. LDT 7 and 01, and here also same thing. Okay, so here we get a 2's complement. Okay, so if we do the target address, which is 1040 minus a PC value, which is the next value 1046, then you will get negative value, right? If you get a negative value, calculate the 2's complement of it in hexadecimal. Okay, so in that way you will get the FFA value, which you will be writing here. Okay, so here also the same thing is there, and Okay, here's something different in 160. So as you can see here, stch buffer comma x. If the command comes in this form comma x, at that time it is indexed. Okay, calculate the target address 0036 minus the next line of this one, it's 1051. You will get a negative value, and when you convert it into hexadecimal value, you will get a value which is greater than 2047. If it is greater than 2047, it is not PC relative. Then go for a base relative, because PC relatives range is 2047, and here you will have minus 2048, I guess. Okay, so if it is greater than this one, it's not in this range, so go for base relative. In base relative, you'll have till 2047's doubles, right, from 0 till 2047 into 2. Okay, you'll have this much range, so it will come in this range, and you'll be taking the b value as 1 and the pc value as 0. Okay, e value is 0 because it's format 3. Okay, so that's all what you'll be doing here, and what answer you get here, that you'll be writing here. Okay, so for that you'll be doing the buffer minus the b value instead of ta minus pc value. Okay, if it's for buffer, you'll be doing buffer minus, buffer is 0036 minus what is the b value. B value is different, it's pc value is the next pc counter value, but b value is 0033. Like that you can see the length store in the base register by seeing the symbol table. Okay, in that you will get the answer 0033. Substitute and subtract, you will get 0003. That answer you will be using here. In another one also, like 175, also here's the same thing happening. If it is greater than the range here, what we are doing, we are going to base relative. In base relative, we'll get an answer which we'll be using here. Okay, so here also the displacement, there is no operand, so we'll be just writing 000. Remember r sub, it was nothing, like we'll be writing it like this dash, right, and that's what it's showing here. And for input byte, and store it as it is, don't do anything. And here also it's increasing, like in 212 the length is increased. So what we do here is, like if the length is increased, go for base relative, and the base relative answer will be writing here. Okay, same as we have discussed in the previous case. Okay, is the same thing, format 3 plus pc relative, same as the previous one. Here it is indexed, so if it is indexed, we'll be checking ta minus pc if it's greater than the length. Again base relative, the same thing which we had discussed earlier also. And here also it's pc relative, and format 3. So r sub is just there, so 000 will be writing. Output byte os is there, so character string, store it as it is, like os only. Okay, so that's all is there in the SIC XE program. After you get those things, this thing is very simple, right? This we have discussed earlier also, how to write. Okay, 3 things will be there: header and t and e. So how to write this one I discussed earlier, means in depth in the previous video, not in the previous video, in the previous topic, which is SIC program. Okay, object program, you can refer that. Okay, so that's all what is there in the SIC XE. Means that program to object code. Then this loading of the memory also is the same as the previous one. And these were the questions which are good for the foundation purpose, but if you understand these type of questions, then you will be easily able to solve the questions which are actually asked in exam. So let's discuss now what are the questions which could come in exam. Okay, the question is to generate the complete object program for the following assembly level program. Okay, so this is the assembly level program which is given to us, and we have to generate an object program, and these are the opcodes given to us. So your first step, you will have to start from here, and you'll have to write these things. So how these things are written: start from here, wherever you find start, and if the operand is 0, that means you have to start from 0. Write the next line also as 0, and then after that you will see what is this one. This has 2 bytes, right? So we'll be writing 2 here. And what about LDA? LDA is immediate addressing, it has 3 bytes, so 2 plus 3, 5. Like that you will keep on going. For the assembler directives you won't write, like base and all, and for the rest of the things you will keep on writing plus 3 plus 3 plus 3, and here it's plus 4 because it is of format 4, because it is plus here, so format 4 will be adding 4 bytes. Okay, rest of the things will be adding 3 bytes. If it's a reserved word, calculate the equivalent hexadecimal value and add it to it. Okay, like that you will keep on adding and writing the length values, sorry, not length, the log ctr values. After you have written the log ctr values, you are supposed to write this one. These things also, like same as we have discussed the previous one, you have to write in the same way. For x it is b4, for clear it is b4, for x it is 1, so you will write here 1 and add 0 here. It is means 0 here, so we'll be writing here as 0. So we'll be writing 1 here because of the object code which we are generating here. So let's discuss each of these one by one. It is the immediate addressing, so 0, you'll be writing here zeros, and these codes you'll be writing, right? In these codes here it's immediate addressing, so you'll be writing 1 here. So because of this will become 1 and 0 0, rest of the things will be 0. For that you have generated this code. Okay, The same we will be doing for the other things as well. Okay, this was for format 4, so we'll be writing here by means plus you'll be understanding if it's format 4 or not. And here it's the indexed addressing, so for x value it is 1 here, and the rest of the things are same as we have discussed in the earlier videos, sorry, in the earlier part of this video. So yeah, here also it's same like that only we have to do. And if it's format 3, by default it's PC relative, so we'll always calculate PC relative value. What is the loop value? It is 12, and JLT value is 9, so we'll be subtracting it and finding out the answer. If it's within the range, we'll be writing here, else we'll be finding out the base relative, right? So the same thing, and the object code is also the same thing how we have written for the previous one, h and e and t's text values here for each, and this is the text length and starting address, same thing as we have done for the previous one. Okay, and you can refer to this symbol table. This will be generated after we have passed from the means after the pass one, this will be generated, right? Loop where we encountered 09 and count where we encountered 016, that will be writing here. Okay, the same thing goes for this also, but this is the SIC program. The previous one was SICXE. Most of the questions are asked in SICXE, but here the only difference is that immediate addressing will not be there. Just have to write means word like this, and this word should be defined in the lower part. And we'll be starting from here. It's 4000, same thing, plus 3 plus 3 plus 3. Wherever it is reserve word and all, we'll be adding that much reserve word value. Finding out the program length here. Two types of modes are there in SIC. X is equal to 0 and x is equal to 1, and the opcode is in this form. There's no format 3 or format 4 and those things, but just standard version of this one. So here we'll be substituting the values, and yeah, that's all what we are doing here. If it's x value, means it's index addressing, right? If it's index addressing, at that time what we have to do, if it's index addressing, we'll just make this x value as 1, and rest of the things we are writing as same. Okay, so yeah, also it's same, and this is the object program. These type of questions you can expect in exam. Okay, so loading into main menu also is as the same as the previous one which I have discussed in the SIC. In the same way we'll be solving for SIC XE also. So here also this is same as the first question, just add 3 here, and whenever it is means format 4, add 4, rest you will be adding 3. If it's a reserve word and all, you'll be adding the equivalent value of it. And these object codes also in the same way we'll be writing. If you want more information, it's present here, you can go through this, but the means the technique remains same. Okay, so that's all. This is also the loading into the memory thing. So this is what you need to know, means most important thing in this module about the SIC XC program to object program. Okay, moving on, here the program relocation. A few theoretical concepts are there. Let's discuss each one by one. So the first one is the program relocation. What does it mean is, suppose that I have started a program from here. By this image only you can understand. The program starts from 0 and ends at 1076. But if I want to relocate it to any other memory location, then this will start from 5000 and this will end at 6076, right? So that is known as program relocation. Okay, so what will be the relative changes, means the relative values between each of these will remain same, means 5006 minus 5000 is same as 06 minus 0, right? So same things will be calculating what are the address for each and will be substituting. That is known as program relocation. There are 5 machine independent features, which are literal, symbol defining statements, expressions, and program blocks and control sections. So here we will be discussing each, what do these terms mean, and how they are applied in the SICXE. So literals are the constant operands which can be stated as like the value of it, literal value of it. For example, if you see here, there is endfill and LDA EOF is label here. What value of EOF you will find is, you will be finding out in this part what where EOF you will find that what is stored as that value, that you will be using that value as, right? But directly also you can specify like by using is equal to sign, is equal to CEOF. Instead of just EOF, you will be writing is equal to CEOF. So the EOF value will be substituted here itself. Okay, and second is the symbol defining statements. For that we'll be using two directives, which is equal and origin. Okay, for equal, how can we use equal is like if you define LDT hash 4096, it can be replaced with max len as equal to 4096. So 4096 value will be stored in max len and LDT will be assigned as max len. So here's how you will be using the EQU origin, means the assembler directive. Next one is here also you can use like this to assign values to the registers. And to reflect the logical function also you can use base equal to r1 or count equal to r2, yes or no, that answer will be output. And origin means assembler directive used to indirectly assign the values to symbols. So origin org value, if you like do the org value, at that time the assembler changes the logctr value to the specified value, whatever value we have specified. Okay, so like for example, value equ stab plus 6. So here's the offset is getting set in the from the stab, like plus 6 and plus 9, and that is for using equ, and to fetch the value field lda value x, where x is equal to this value for each entry, and this is the index register. Okay, so org is not much used, but if you use like org, at that time the value will be set as logctr's value. Okay, so here is the size of each field which is specified, and to restore log value will be adding this number here. Okay, the third one is the expressions. Expressions are like the arithmetic expression plus minus into divide, and the expressions are classified as absolute expressions and relative expressions based on the type of the value produced. Absolute expression means the program location will contain absolute terms like the constants. Relative expression means it will not contain the actual values, but like the variables it will contain. Okay, this is the absolute, this is the relative. Okay, and then the last one is the program blocks and control sections. Program blocks is nothing but the blocks of program here. Okay, like block 1 and block 2 and so on. Okay, so these are the advantages of it. And how do we use it is by using the keyword use. Okay, use block name. If you specify like use c data, c data is a block specified in the later part of the program. If you write use c data, that whatever the program block has been specified, that will be used here. Okay, there are three blocks in the program. Unnamed program block contains the executable instruction of the program. C data program contains all the data area, consists of a few blocks of memory, few words which is preserved. And C blocks contain all the data areas that are contained in the larger blocks of the memory. So here, as you can see, from this address to this address is default. C data starts loading from here, and C block starts loading from here. Okay, these are the reserved memory blocks for the execution. Okay, and a control section is a part of the program that maintains its identity after the assembly. Each such control section can be loaded and reloaded independently of others. Okay, so here's how control section looks like. There will be a linking between each of these memory locations, and that will be stored in a different part of the program. This has relative address. This is the source program and object program. Okay, this is known as control sections. It has the links between the different parts of program. So these were the main features which are the machine independent features in SIC XE. Moving on, we have assembler design options. The two types are one pass assembler and multi-pass assembler. One pass assembler means will be just passing it once and executing the whole program. How does this work is by initially defining what are the opcodes that are to be used. If we do not define the opcodes, first we'll find out the opcodes in the first pass. In second pass, we will substitute those opcodes and find out the answer. For that, only two passes is used. But instead, if you just refer to the opcodes which are previously present, at that time only one pass is sufficient, isn't it? So that is known as one pass assembler. That is known as load and go algorithm. Okay. And multipass assembler, why does multipass assembler need is suppose that we start from here, alpha equals beta, I don't know what is beta, beta equals delta, I don't know what is delta, delta is equal to 1, reserve byte 1. So here from the first pass I'll get to know the value of delta. In second pass I'll get to know the value of beta, but still I'll not get to know the value of alpha in the second pass. In third pass I'll get to know the value of alpha as well. So here three passes are required based on number of unknowns, right? So how many passes are required based on the number of unknowns is known as multipass assembler. Okay, so these are the dependencies which are present, and each time we'll be passing through it and will be substituting the values of unknown values here. Okay, so how many passes are needed based it's depending on how many undefined symbols are there. Okay, so what are the basic loader functions? A loader is a system program that performs the loading function. Okay, loading function means as we had discussed in the previous also, object program, how it is stored in the memory, that one I had discussed earlier, right? In the first SIC program, that same thing is here. This is the function copy which is stored in the memory. Here you have the address values from A to F, and here you have the address values means 1010 is incrementing here. Okay, so that's how you store the address values. And if I consider an example here, it's the starting one is 141033, then 4B2039. So here also the starting one is 141033, and here 482039. Like that, here how many it is there, like 8 bits are there, 8 bits, 8 bits, and so on. In that way it is stored. Okay, that is known as loading, or loading the object program into the memory. Okay, so here's the algorithm for the absolute loader. This is also an exam for the bootstrap loader, but absolute loader is also very similar to it. So here what's happening: begin, read the header record, means what is the header record is present here, verify the program name and length. So what is the header record here? This is the header record, this line, and here we have the object name and the starting address and the object length, means the program length. So those things will verify the program name and length. Read the first text record. First text record is which one? This one. This one is the first text record. We will be reading this one. When we read this one, at that time, if it's not equal to e, means it's not equal to end. At that time, if the object code is in character form, convert into an internal representation. Move the object code into a specified location in the memory. Read the next object program record. Means if when you will read one of the codes here, at that time you will be inserting that in the specific memory location. Then you will read this one and insert here. You will read this one and insert here. Like that only it happens till the end of the program. Okay, so that's all what is the algorithm for the absolute loader. And a simple bootstrap loader. What is a bootstrap loader? When a computer is first turned on or restored, a special type of absolute loader called the bootstrap loader is executed. It begins at address 0. It loads the operating system at address 80. The object code from the device F1 is always loaded into the consecutive bytes of the memory, starting at address 80. Means when you switch on the computer, at that time a program will be loaded from the address 0. It begins at address 0, but the operating system will be loaded at address 80 from the device F1. After all the object code from the device F1 has been loaded, bootstrap jumps to the address 80 where the it begins the execution. Means computer has turned on, bootstrap has started, it has loaded some program from 80. After this is done, means total loading is happened, it will start executing this code. Okay, so much of the loading performs means operation happens from the getC, which is get character. It reads each character, this is the algorithm, and converts into ASCII value to hexadecimal value are represented by the characters. If the ASCII code for 0 is means ASCII code is 30, hexadecimal is 30, it is converted to 0, and the same goes for other character as well. Okay, and getC is used to convert a pair of characters from device F1, and two hexadecimal values considered, like 1 and 4 can be written as 1 for itself. Okay, means in the hexadecimal values, two numbers can be represented as a single byte. Why? Because a byte means 8 bits. So 1 can be represented as 0001, 4 can be represented as 0100. So how many bits are there? 4, which is 8 bits. 8 bits is nothing but 1 byte. So 1 byte can be represented in this form 1 4. Two numbers can be represented. Okay. Along with that, STCH and TIX are used. This for the increment and the comparing operation, and this for storing the indexed memory locations. Okay. And if you see the actual bootstrap program here, it's the device code which is read from the device F1 and enters into the memory. After that that has been done, and then the next address will be loaded. Like for example, here the subroutine to read one character from the input device and convert it from the ASCII code to hexadecimal. Read one character, convert from ASCII code to hexadecimal digit. The converted digit is then returned in a register A. When an end of the file is read, the control is transferred to the starting address hex 80. Okay. That is the program which we'll be seeing, like just taking a input and storing it to the register A after conversion which happens. Okay, so clear A will be cleared as 0. LDX load into register X as 128, which is hexa equivalent of 80. So get the character from the program, save it in register S, and after that move to the higher order of the bit, get the next hex digit, combine the digit to form 1 byte. 2 digits we need to form 1 byte, so 2 digits will be there, like 14, and that will be stored here. Store the answer in the X register, and after that add 1 to the memory address, means go to the next memory address and do the same thing until you reach 128. Okay, and this is the subroutine which is getting called here, which is a subroutine getC. How does getC actually work? That's defined here. Okay, because we are calling getC and just telling that a character is read, but how actually the character is read, that will be seen here. Okay, so first we will test the input device. If it's equal means we will be stopping it. If it's less than, then it means it's ready. So we'll be reading one input and comparing with 4. The hexa character is 4, means it's end of the file. If it's not 4, at that time only we will be executing. If it's equal to 4, go to 80, that means the end of the program. We will be starting from here, then we'll be comparing with 48, because hexadecimal character, if it is 0, then we'll be ending the program. If it is less than, then skip to the next part here, subtract 48 from the ASCII code. Okay, and compare it with 10. If it's less than 10, conversion is complete, means greater than 10 only we need to convert into alphabet, right? Else from less than 10, what is the value, numeric value, that is the same as the numeric value, right? After this is done, we will be returning to the subcolumn, means from where we had called the function, means from here, After the get C is done, the character is taken and converted to hexadecimal in the character taking itself. That's saved in the register S. Okay. And xf1 is the code for the input device, and end loop. After this is over, then end the loop. Okay, so this is what is there in like important things in module 1. And the most important thing is the SIC XE program to the object program code, and practice more of those questions. And yeah, that's all for this video, and thank you so much for watching. I'll see you in the next one.